Urso, please help fold and distribute the cards. I'm gonna have to stand with. I'm gonna have to bend over.
That's awesome. That's great. My wife's style. Yeah, yeah. And the Savannah Clean, I believe is what it's called, the boat. Oh, yeah. Power coming up here, and that's really cool. That's really nice.
This says if we have technical issues, we should call somebody named Carolyn. Not you?
Carolina AV, yeah,
Okay.
we used to get a call and you say, I have no idea what we're on this. I have no idea. So yeah, we put that on Carolina. Yeah, Carolina AV. City Hall. Before we get started, we got some first aid equipment up here. Reagents are here and there. We'll do emergency, call 911. If you have any questions, we want to keep it real informal. Don't hesitate. Raise your hand, speak up. Anything you want to know about or you might have, we've got a group here that can certainly address it. I'll put them on the spot, tell them they can handle anything. But no, we are really glad you could be here, and with that, I'll hand it over to Mark.
Good afternoon, everyone. Hope you're doing well after lunch. It was really well, and I hope I'll be able to keep you guys awake. Well, me and Trevor can keep you guys awake for this afternoon session. My name is Mark Miller. I work for GeoEngineers. I started as an intern for them in 1996, and I've been there ever since, so kind of a lifer at this point. I got a bachelor's degree in geology and a master's degree in geotechnical engineering, and I started getting into horizontal directional drilling, trenchless technologies in about 2005. So really found it interesting and just kind of made my career out of that, kind of transitioned into it. Trevor Hoyles, he'll be presenting today as well. We're going to kind of switch off, and so I'll let him introduce himself after I'm done here with my first session. So anyway, Trevor, you want to hit the next slide? So hopefully today, I think you skipped one. Okay. So we're going to start with what is HDD, and I mean, this is very basic, and we're going to get into more details, and hopefully we're going to teach you guys some things that you didn't know before, and hopefully also give you guys some things to think about when you have a project that's got a drill on it, some of the design principles, some of the construction concerns, things like that. So anyway, we missed our safety moment. Anyway, I had a safety moment, but evidently that's weird. Anyway, so what is an HDD? So you got a pipeline, some other type of utility. You need to get across some sort of obstacle. Here we got a river, small river, but you don't want to open cut across that. So we'll just drill under it. So here you got an entry workspace on this side. It's nice and big, got plenty of room for equipment. Over there on the far side of the river, you've got your exit point. You can see that beyond the exit point, you've got see if this works. Beyond the exit point, can you hear me? Beyond the exit point, you've got your stringing area for fabricating and stringing your pipe. You can see it runs back up in there. And next slide. So we're going to show a little video. This is just a very basic kind of, I think this thing's got to be like 15 years old, but it kind of gives you an idea of the, and you can't hear the audio, and there's no one controlling the computer right now. So anyways, you can see you got a river crossing here. First thing you're going to do is you're going to drill a small diameter pilot hole from one side to the other, directionally steered. There's kind of we'll show some more of this, and I'll explain some of the parts and pieces that you're seeing there. You ream the hole out to the desired size. So here you go. You're reaming the hole out. Various different types of tools can be used for reaming. And then you pull the pipe through. So we're going to show a lot of pictures of types of tooling. Here's pulling the pipe through. I'll explain all this stuff, what it is, why you have it here later. So construction process. So here's kind of typically starts up, rigging up equipment. This is like a 440,000 pound American augers, DD 440 drill rig. You got a trailer full of drill pipes sitting here. You've got the drill cab. Some of the smaller rigs you'll see will have a drill cab attached directly to the drill rig. You've got a cleaning system set up back here. This one's kind of a tight workspace from side to side, but it's doable. Usually when they're rigging up, they'll also be, if they're using a magnetic downhole steering tool, they'll also set up a survey coil wire set up on the ground. So on larger, more complex drills, they're going to use a downhole steering tool, which uses Earth's magnetic and gravitational fields to actually determine where it's at underground, which there is some room for some interference with the magnetic sensors within the steering tool. And so by setting up a coil wire along your alignment, such as this, you can see this wire goes up to this truck. Well, that's a DC welder, and you put a DC current through this wire. So this creates a magnetic field. You can see these little lines here. This creates a magnetic field that the steering tool can pick up. So basically, you're replacing the Earth's magnetic field with your own that you create with this wire and a current through it. So it's not susceptible to interference. So that's kind of nice. However, this slide here shows the wire going across the river, which you can do that in some cases, but if you get a really wide river crossing or it's deep, it's not really feasible to run your wire across the river. So what you end up doing is you have two smaller coils just on the land portions on both sides, and you have to drill the river portion without any sort of secondary check. So normally you'll have the steering tool data using magnetic and gravitational field of the Earth, and then you'll have this as a secondary check. So when you're drilling across the river with no coil in the middle, then it's what they call drilling blind. So you're just using the tool itself. You have no secondary check. Okay, this shows a drill rig setup. They're set up to drill pilot hole. This whole thing from the spindle on the carriage down to the drill bit, that's called the bottom hole assembly, and we'll see more pictures of that, and I'll show you the different pieces and parts and how it all goes together coming up. So this is a little bit closer shot, this little cartoon. Can you hit the clicker? Because I think it should give a little animation thing. So basically, you've got a drill bit in front. We'll look at different styles of drill bits. This is for soil now. So this has a jetting sub. We'll talk about how rock is drilled later, talk about that. So you've got a jetting sub here. You can see it's at a slight angle. There's a slight bend here to this piece. So it's got threads that are cut on an angle. Here you've got an orientation sub, and then you've got an annular pressure port. So when we talk about annular pressures later, there's a pressure port here, and this pressure port is connected to the steering probe, downhole steering probe, which sits inside this non-magnetic drill collar. So this is sometimes called a Monel. And the reason for this being non-magnetic is that these steering tools, these magnetic steering tools, can be affected by steel. The readings can be affected by steel. So this thing's non-magnetic. There's a material called Monel, which is a type of stainless steel. The steering probe sits back here so that it's not affected by the steel up here in the bit and all this other stuff. So, and like I said, we'll get into more how this all works a little bit later, but Trevor, next one. You can also drill up and intersect. You can drill pilot holes from both sides and intersect them. So on a really long crossing, you get out 4,000 or 5,000 feet, it can get hard to steer. So one thing you can do is you can drill from both sides, intersect the two holes somewhere in the middle, and effectively kind of shorten the crossing by about half. Really helps with steering. And also, by doing this, you help reduce your risk of frac outs or inadvertent returns, because basically the further you drill away from the rig, the higher your pressures are going to get to maintain your circulation back to the drill rig. So if you can drill half of it from each side, you can kind of keep your drilling fluid pressures lower than you would if you tried to drill it all from one side. So there's a pilot hole bit punching out. You can see the stake there. So these survey systems are pretty accurate, you know, as long as they're not having issues with trying to steer. You got a competent crew, they can typically knock the stake over. This is reaming. Oh, hey again, Trevor. So it's reaming. So typically you would punch the pilot hole out and you would pull the reamer back towards the drill rig. So you can see you've got drill pipe in front, they're pulling, they're rotating the reamer. While they're reaming, they're pumping fluid down the drill pipe. It's coming out, the reamer, it's shooting out. They got jets in the face of this thing. And it's basically just blasting the soil away. It's eroding the soil away. It's mixing up, the fluid's mixing with the cuttings, and the cuttings are typically flowing back to the other side. You know, it's the path of least resistance. You got a bigger hole, the fluid's going to want to go back this direction until you get closer to the rig, and then the returns will start coming back to this side. And then you got your, that's all right. Then you got your tail string. So tail string basically attached to the back of the reamer on smaller projects. Sometimes they don't use this. On larger crossings, you're going to want to use a tail string, because if you break the drill pipe in front of the reamer and you don't have a tail string, you're going to have a hard time getting that tool back out of the ground. But if you've got a tail string coming back out to this side, well, then you got something to attach onto and try to pull that thing back out the backside. Thing is, with that, you're going to have some crew over here. You're going to have some equipment over here. So it's more work, but it can save you if you do have a problem. Just showing a reamer. Looks like a split bit hole opener used for rock crossing. Looks like they're just getting ready to start a ream pass. Swabbing. So once your reaming passes are done, you've got the hole as large as you need it to be. You'll just run a swab tool through here, which is smaller than the hole, but bigger than the pipe you're going to pull. And you're basically just going through there, pulling it, checking for any spots where your rotary torque is high, your pull force is high. You might have some accumulated cuttings down there. You might have some sections of the hole that have maybe had some instability and collapsed. This kind of gives you an idea of how ready that hole is to pull a pipe through it. So you may decide, well, look, we should probably do another swab pass just to be safe, or maybe even a larger ream pass. So that's just showing it. You should go ahead to the next one. Pullback. So we talked about that a little bit. So a typical pullback assembly, this kind of whole thing here, you've got a reamer sitting in front. So that again helps if you do have some accumulated stuff down there, it can help clear it out of the way. You got a swivel. This allows them to rotate the reamer and the drill string without having to rotate the whole pipe. Then you've got the pull head with a pad eye on it. It's all hooked together, and the pipe follows. So you can just hit the next one.
Yeah, I just want to mention, you did mention earlier, anybody feel free to ask questions as we go. It's really meant to be interactive. No dumb questions. There's a lot involved in this, so yeah, feel free to ask away.
Yeah, and speak up because I'm too busy looking at the screen and pointing at stuff, so I may not. If you raise your hand, I might not see you.
On the reaming, some operators might push ream.
That's a good point. Yeah, I did not mention that. Some operators do like to push ream. One reason for that is when you push ream, your drilling fluid's coming back to the rig for the most part, which is you've already got a cleaning system and pump and everything set up on that side to handle and recycle the fluid. If you pull ream, most of your returns are going to be going to the exit side. So now you've got to have equipment or some way to transfer fluid from the exit side back to the entry side where your pump and your cleaning system and all that are. So there are some advantages to push reaming for sure. Yeah, good point. This is just showing pullback. You can see here, you got the pipe coming out of the ground, or going in actually, I should say. And you can see the pipe, the overbend or the breakover, some people call it, being supported by some side booms here. And you actually see what they did here is they dug a tail ditch back here, because the exit point was originally around here somewhere, but by digging this tail ditch, they're able to get this pipe lowered down and get the ultimate height of this overbend lowered to the point where they could actually handle this thing with side booms. So they kind of did themselves a favor by doing that, because otherwise you might have had to get some cranes out there to handle this thing. So let's talk about tooling, talk about different types of drill bits for pile hole. Go ahead, Trevor. We'll look at these a little more closely. Okay, this is a tricone mill tooth. So these are milled teeth, tricone, because there's 3 of them. You can see there's a drilling fluid jet right there. There's one there, and there's one over here you can't quite see. That's where the drilling fluid comes out. And when you're drilling soil, essentially you're relying on this fluid coming out of the jets here to actually cut through the soil. The drill bit on a soil crossing doesn't do a lot. Now you could use this on a soft rock too, like a soft siltstone, things like that. This bit would be sufficient for that type of crossing. Okay, so this is a tricone bit with tungsten carbide inserts. So this would be for hard rock crossing. You can see again, you got 3 jets there. So same concept, just for harder material. Go ahead. I don't know, I call this a duck bill, I guess. It's usually used on smaller track mounted rigs for little crossings. It's just got a bent end on it, and these are drilling fluid jets. It steers very well. So you see these on a lot of smaller crossings, like little utility crossings, things like that. Okay, so let's talk about the Monel. We talked about that a little bit, the jetting assembly. So these 2 things make up what's called the bottom hole assembly, okay? This is the non-magnetic piece. This is the jetting assembly, which screws on the front of it. And you'll see this little protrusion here. The steering probe actually gets loaded. And actually, just go to the next one. I've got another slide we'll show here. There's the jetting assembly. You can see this. The probe actually screws into here, and I'll explain how that all fits together. Go ahead. So you can see this has about a 2.5 degree bend in it. So like I said before, the threads are cut at an angle. This will range from, I want to say about 1.75 degrees to around 3. There's probably some less, some more. 2.5 is pretty typical. So this is what's made up. So closer shot. So you got your drill bit. This is our bent sub or jetting sub. You can see it's kind of at an angle there. So this is our orientation sub right here that we showed earlier. There's the pressure port we showed, and then this is the Monel, the front of the Monel. So essentially your steering probe gets loaded into the Monel. It's got centralizers on it, so it keeps it in the middle. And then that little stinger part, that protrusion on the back of the orientation sub screws into the front of the probe, which is then connected to this pressure port. So as you're pumping fluid, it's going back up the hole through the annulus. The annular pressure is sensed through that port right there. And you can see, like I said, it's kind of got a bend to it, slight 2.5 degree bend. So some of you may be asking, well, it seems pretty rudimentary, so how do they steer this thing? So that steering probe that's back there in the Monel, it's got a roll sensor. And so see what they do is they get this all made up, they'll stick it on the drill rig, and then they'll do what they call high side. They'll rotate that bend so that it's straight up. And then inside the driller's cab, because there's a wire coming off the back of the steering probe back here. It's a couple feet long. So the wire runs all the way back up the drill pipe, and it goes into the drill cab. There's a driller's console which shows what we call the tool face. It goes from 0, being straight up, to 360, being all the way around 360 degrees. So when you high side the thing, you rotate it to high side, and then you zero the roll sensor. So now the driller knows when that thing's 1,000 feet down hole or wherever it's at, he knows which direction that drill bit's pointed. So if he needs to go right, he rotates it to 90 degrees. And then for soil, essentially, like I said before, you're using drilling fluid pressure and flow to erode or cut the soil. Just turns the pumps on and pushes it. And he may have to push it 5 feet, he may have to push it 8 feet, 10 feet, 15 feet to get the amount of steering that he needs. Just depends on the formation, depends on the bend angle of his jetting assembly, depends on several things. And then if he wants to go straight, he just rotates the whole drill string and just pushes it down. And theoretically, it should go straight. So that's how they steer it. Trevor? So these are mud motors, positive displacement mud motors used in rock. You can see they're pretty long. So you've got a power section up here. So as you pump drilling fluid through this thing, this power section, there's a rotor and a stator inside here, which causes a shaft to turn. That shaft goes through a transmission down here to the bit box. Bit box turns the drill bit. Now this one is a fixed housing. So you can see it's got a bend to it, but you can't adjust it. This motor, on the other hand, has some adjustment rings where you can actually adjust. It's called adjustable housing motor. You can adjust the bend angle on it to steer more or less aggressively. And here you can see a better picture of the bit box. So this orange piece is what spins the bit.
Mark, you want to clarify when a contractor would use a mud motor versus a jetting assembly?
Yeah, so jetting assembly is good for most soils, although you get some really hard, like glacially over-consolidated soils, like glacial till. A mud motor could be used in those. One of the problems is in soils or dense sands. We've seen Mississippi River crossings done with mud motors because they're very, very dense sands under the river. So mud motor can be helpful, but in soft soil conditions, a mud motor as part of your bottom hole assembly, it's pretty heavy, and so it's harder to steer. And it can be harder to steer in soils. So you typically wouldn't use one of these in soils. So there's kind of a cross section of one. Like I said, there's the rotor, the stator, this power section. You pump the fluid through, causes this section to turn, turns the shaft. There's a transmission, gear reduction, and the bit box down here. Go ahead. Let's talk about reaming and swabbing tools. So this is a split bit hole opener. So this would be for hard rock. It's got tungsten carbide inserts on the cones. So the bigger you get, the bigger the cones get, the more cones you have. You can see it's got a threaded box on the end and a threaded box on the back for a tail string, like we saw earlier. This thing I call beaver tail. You'll see these a lot on smaller rigs, but I think I've seen some bigger ones up to like 36 inches, and they work good in really highly plastic clays because this thing helps. It's like an egg beater type thing, cake mixer, and it mixes the clay with the drilling fluid a lot better. So it helps mix those cuttings in with the fluid so that the cuttings don't fall out, they don't start sticking together. We'll talk about that a little more later too. It's considered just like a ring style fly cutter. You know, a lot of companies will actually make these in their shop. Bigger drilling companies will just make these. Those just most soil formations you can use those, except in clays. These can get all plugged up with clay, and then just kind of, I don't know, they're just not as effective, I think, sometimes. You've got a barrel reamer here, just a barrel with some teeth on it, basically. You use this for swabbing the hole a lot of times because you're not trying to cut anything really. You're just trying to run something through there, break up any cuttings that have accumulated, flush them out. I'm not sure what this thing's called. That's kind of crazy. Like, I don't know where, you know where this came from? Okay, this is a job in South Carolina. I've never seen one of these in person. That's right. And then it's just kind of another fly cutter style reamer. Okay, Trevor. Pretty much, yeah. The style is based on soil type. Even the hole openers like this one. This one's made by Southeast. They make a lot of their own hole openers. And the cones, the style of the cones, the spacing of the teeth, all that stuff is just kind of dependent on the formation. Different manufacturers have different ways of doing it, but yeah, pretty much. Talk about pullback and kind of the pullback assembly here. This is a 48-inch pipe in outside of Tbilisi in the country of Georgia. This was a BP project back in 2005. So you can see a barrel reamer in front. You can't see the swivel. You got the pull head. You got tons of side booms. There's a kind of a closer picture of similar deal, smaller pipe, hole opener, swivel, pad eye, pull head, and then pipe. Of course, you got your pipe rollers. Here's another picture. This one doesn't have a reamer in it, but in reality, I mean, you look at the size of the drill pipe and the size of the pipe they're pulling, the swivel is bigger than the pipe. So that's kind of your reamer that you would typically put in a pullback assembly. So we'll talk about cuttings removal and how that's done, kind of explain the whole cleaning system here. So here's kind of a typical big, you know, they typically clean these things are about capable of handling about 1,000 gallons a minute. That's a little optimistic, but so what happens is when you get your drilling fluid returns, you're pumping fluid downhole, you're cutting the formation, the returns are coming back. Those returns now have cuttings in them. You want to reuse the fluid, so you got to separate the solids from the fluid. So the first thing it does is the drilling fluid dumps into this thing right here. So this is a shaker bed. This is called the scalper. So it's the first pass the drilling fluid makes through this system. And it's got screens, basically like sieves. Essentially, they're just big sieve screens. There's typically like 3 big sieve screens on there. And they have relatively large openings. So this catches all the big stuff. So all the big stuff hits the screen. These things vibrate. These things kind of have these eccentrically weighted motors, and this thing vibrates, and the solids just kind of walk off the side here. And I believe, I don't know, so you might be able to, but typically they'll put a bin here, like a roll-off container right here to catch them. So they're setting up, they're rigging up, right? So they haven't got that far. Once the drilling fluid goes through these screens, it gets pumped up to this thing, which is called a desander. Now this has what are called hydroclones. It's kind of like the same principle as those Dyson vacuums. Same principle, except these are hydroclones in that they're made for fluid. So the fluid goes into these things, it spins around really fast. The fluid tends to go up, and the heavier stuff, the solids, goes down, and it comes out the bottom of those hydroclones. Again, hits a set of screens. This time these screens are a bit smaller mesh, so it catches a bit smaller material in the scalper. Again, that stuff falls off there. And then this is the desilter. So this has a bunch of hydroclones. They're smaller. They're made to separate out finer material. Hits the shaker bed. Solids come off the side, and the fluid goes down into the tank here, which can then be pumped back downhole through your high-pressure drilling fluid pump. This is a triplex pump. So. And then, of course, generator on the whole thing. So here's what it looks like in operation. You got the scalper, the bigger stuff. You got this desanders, kind of the sandy size material. And then you got the desilter, so that's the fine grain stuff. And then, you know, they can change the size of screens depending on what they're drilling through to kind of optimize the cleaning. You see you're getting a lot of flashing here on this one. You get a lot of liquid coming off. So maybe if they change their screens a little bit, they could reduce some of that. But there's just another picture. Here they just dug a pit. So the cuttings are going to that, and then they'll have to haul that off as they go. Talk a little bit about basic geometry. So this is the most basic thing. Typically have an entry tangent. You know, depending on the size and scale of your project, you know, this may be less than 60 foot, maybe a lot more than 120 feet. But the nice thing about having some straight entry tangent, of course, this is not to scale, right? It's way steeper. 8 to 12 degrees is pretty typical. But the reason why you want to have some straight entry tangent is when you first drill into the ground, you want to get in a little ways before you have to start steering the drill bit. You want to get down into some maybe denser material, higher strength material. And you also want to give the pile hole surveyor some distance and the driller some distance to kind of feel it out before they have to start making their curve, which, Trevor, you got your entry curve. So, you know, they got to turn this thing horizontal at some point. So before you start this curve, you know, give them some distance to get into some maybe better material, get a feel for things, and then start the entry curve. So, and these are just kind of rules of thumb. I mean, obviously, this can vary widely, but typically it's nice to have a bottom tangent, you know, of some length, because, you know, as they steer through this curve, if maybe the thing's not steering as effectively as they want or need to, you know, they may end up down here. And so by having some straight tangent section, that allows them to catch back up and get back online. You know, if this thing was just one giant curve, it'd be a lot harder to catch back up. So then you got your exit curve, similar deal, and then you have your exit tangent, you know, and the exit angle here will vary. We'll talk about that a little bit more later, but go ahead. So this is kind of a typical plan profile design drawing. You can see entry point, we got a straight tangent section coming down to here. We got our curve, we got a nice long bottom tangent. I think this was 4,000 feet or something, I don't know. And then you got the exit curve here, and then you've got your exit tangent. And here you can see there's some existing pipeline that was drilled, and we'll talk more about, you know, some of those considerations about separations and things like that. I think that's question. Yes, ma'am. Okay, so what stage is the bentonite added and where? So essentially all the drilling fluid is bentonite based. It's about, I want to say about 97% water and about 3% bentonite. So it's always in the drilling fluid system. Yeah, and then so, you know, they may have some additional additives in there as well. Some polymers and stuff that kind of help the viscosity and the cuttings carrying capacity. I'm not a drilling fluids engineer, so I don't want to get too deep into it, but what's that? Like the additives, you mean? Bentonite. Oh, the bentonite? Oh, that's from the very beginning, from the first time the drill bit goes into the ground to the end of it. Yep.
Yeah, I mean, that's what's used to carry the cuttings out of the hole.
Yeah, the nice thing is the bentonite makes a pretty thick viscosity fluid that helps suspend those cuttings. So once you're drilling, the cuttings are getting mixed in with the fluid, and it allows the cuttings to stay in suspension so that you can actually get them out of the hole. So if you don't have good drilling fluid properties, those cuttings fall out, they end up staying in the hole, and then your hole can get plugged up, and so, or your, go ahead. Okay, so inverted returns. You're getting ahead of us, but that's fine. I'll answer that. Yeah. Yeah, no, that's fine. That's a good question. No, but it's typically near entry and exit a lot of times because at the ends of the drill, you're relatively shallow. You have very little soil cover or any kind of cover over top of the profile. And typically those shallower soil zones, they're weaker. So you typically tend to have frac outs near entry and exit, you know, within about 50 to 100 feet of entry and exit's pretty typical. But, you know, they can happen anywhere, so.
And one thing I wanted to clarify, really there's, you know, two primary functions of the drilling fluid. One is to carry the cuttings out of the hole, The other is to form kind of a wall cake around the hole in order to hold the hole open. Because then you don't have any kind of casing or anything to keep that hole.
Yeah. And one of the things to think about too is, the drilling fluid's slightly denser than water, right? So if your hole is entirely full of fluid, there's a positive pressure in the hole relative to the groundwater on the outside. So it helps keep the groundwater out of the hole. So it provides a little bit of positive pressure inside relative to groundwater pressure outside. So, sorry. Thanks, Trevor. Yes, sir. Air hammers, those can be used on for pilot hole. They make some for reaming. I don't have a lot of experience with them. I've heard some people say they work great. Some people say they have a lot of problems with them because mechanically they can have some problems. You need a lot of air. So you need, on a bigger crossing, larger diameter tools, you need tons of air. So you may need like 2 giant air compressors to run everything. But personally, I don't have any experience with the air rotary stuff. What's that? Oh, okay. You're talking about a pneumatic hammer for. Yeah, so we've seen pneumatic hammers used on pullback before, and we'll talk about that. But yeah, so you can use it to hammer a pipe in. Typically, if you're that stuck, you'd probably be using it to hammer the pipe back out. So
Something's not gone well.
up to that point. Name's not familiar. I don't know him personally, no. I know a lot of contractors have their equipment, but I've never met him. So.
We're more believers in trying to get the hole prepared well and spot. I mean, if they're encountering so much. Yeah.
Oh, geez. Yeah, you'll see. You stick around long enough, you see some stuff you never expect to, right? Trevor, you're up.
Yep.
So Trevor Hoyles, he'll introduce himself.
Hey guys, I'm Trevor Hoyles with GeoEngineers, principal with the company, pipelines group leader out of Raleigh, North Carolina. All right, so we're going to talk about sort of the due diligence and planning phase that has to go into an HDD project. So there's several steps that we need to take care of in the planning phase. First thing we do is desktop study, look at everything we can from the office, preliminary evaluation. Then we do preliminary conceptual geometric design. I mean, it may be that an HDD is not even geometrically feasible. So before we jump into advanced design, we're going to do just some preliminary layout to see if an HDD can fit in the space that you have. Then once it passed that test, then we'll go out and do a site visit, do the due diligence out on site, make sure there aren't any surprises out on the ground, make sure we've got some adequate workspace that can fit our equipment. And then we'll go ahead and proceed with the geotechnical borings, getting the subsurface data that's needed. At the end of the day, there's a lot of analysis that goes into the design and the hydraulic fracture analysis and inadvertent returns analysis, and you need good geotechnical data for that. And then once we get the samples, we submit that to the lab, get a variety of lab tests, and all of this I'll go over in detail. And then at the end of all of that, then we should have an idea of whether or not we have a feasible HDD project. And provided it's feasible, we'll move on to the next few phases. One thing that I'd like to stress on the routing, a lot of times we are asked to design an HDD, and we're handed a fully baked route with center line and PIs, and everything's quite well down the road of planning a pipeline project. But what we find is, oh geez, we've got 200 feet between PIs that we're being asked to fit an HDD that requires 700 feet or 1,000 feet. So we recommend that you get your design engineer, your HDD design engineer, involved in the routing stage early to make sure you got space. Not all the time do you have really a choice in the matter. I mean, in this type of situation, this is a greenfield cross-country route, and there's a few different options we can look at here. I know a lot of your guys' projects follow existing city streets and whatnot, and you just don't have a lot of choice in the matter. But it is good to get some ideas there early, and for example, here, this is a longer shot, but we're right up against this head wall on the other side of the river, and we got no space to come up on the other side of that river there. Here, it's a shorter distance, but we got a little bit more room between our PIs on either side. So, and those are some of the just considerations that we make there. So the first thing we do is draw out a conceptual profile for what we think is needed. We're generally given an easement. And really what we're looking at oftentimes are the features that we're crossing. Oftentimes it's a sensitive environmental feature. In this case, this is a stream. And so we know that we're going to have an adequate safety factor against IRs underneath that sensitive feature. So we initially set up a profile that we think is going to give us the depth we need under that feature. And so you got to set your entry and exit points back far enough so that you have the depth that you're going to need over the full width of that feature, including any adjacent wetlands. So that's the first thing you do. And if you don't have the space for that, then you got to go back and have a conversation about other options. Okay, next. Yeah. The maximum length, it depends on the diameter, really about 10,000 feet. Things get really, yeah, that's the max we've ever done is 13,000 feet. Much over 4,000 or 5,000. Mark mentioned pilot hole intersect methods. So you'd definitely be looking at pilot hole intersect. But yeah, they can get quite long. And with regard to the length, the cards that you all had there at your desks, it basically, one of them is for plastic pipe, the other one is for steel. But it's just kind of a very rule of thumb cheat sheet on how much length you need for various HDD crossings of different pipe diameter. So I apologize. The steel pipe one we have there, I think only goes down to 12-inch. I know we've got some folks that put in smaller pipe than that, but this at least gives you a ballpark. HML is horizontal length, and then MD is the depth. So that just gives you a general idea. Next. I'm sorry, what was that? Right. Yeah. No, one of the cards we've got is for plastic pipe, so it's got some shorter length, smaller rig stuff. Yeah. Yeah, we're doing a lot more smaller pipe than we used to. We used to do almost all transmission pipeline. Now we're doing a lot more distribution, smaller plastics pipe as well. So we then move in, once we have a conceptual profile, we think something is geometrically feasible. Then we're going to look into the due diligence on the desktop study. We're going to pull up a geologic map, see what's mapped there in the subsurface. You know, the initial profile that I showed, you know, maybe that we see some geologic units that leads us to believe we're going to have to go deeper. You know, so we might make some adjustments to our profile. We also might consider the geologic mapping in terms of our layout for our geotechnical borings. So that's definitely something to consider. Next. And then we look at good old Google Earth is always comes in handy. We look at the aerial photographs. We look at present day photographs. The historical photographs that show up in Google Earth are often sometimes very handy because it shows past construction, past above ground. Right. Yeah. I mean, so you can see previous construction activities and structures on site that are maybe no longer there, but could mean that there's some subsurface obstructions on site. So we do a full search back on the historical photographs. The street view is pretty handy. That's available on Google Earth. And then we move on to laying out our subsurface exploration program for the geotechnical borings. So once we have our conceptual profile here and it's still looking all good, then we want to lay out some conceptual boring locations. There's been a lot of discussion about, okay, how many borings should we get? And I wish I could say there was some magic number, but there's not. In general, the more borings you get, the less risk there is during construction. And it's really a balancing act, and it also is based on professional judgment with the complexity of the geology, the complexity of the landscape. I mean, if you're in nothing but an alluvial valley with the same material all the way across, you might need less borings. If you go from an alluvial valley to a bedrock hill slope to some other type of formation, you might need more borings. So the more changing conditions you have, the more you're going to want to show that through your geotechnical explorations. But I just got some more on that. So some things to keep in mind, though, you know, first of all, we never would recommend doing one with less than 2 borings. You want one at least one on each end. We typically would do only 2 borings for relatively short crossings, say, you know, 500-600 feet or less. And then just rule of thumb, you know, we're typically somewhere around every 500 lineal feet of HDD is oftentimes where we end up for the amount of borings. For the depth of the borings, I'd say that's the biggest challenge. If we aren't involved in getting the geotechnical data for the HDDs we're designing, that's a pretty common issue that we have. Somebody will give us a geotechnical report from somebody else, and the bane of our existence is borings that are too shallow. You know, because we'll be talking in depth about IRs and our hydraulic fracture analysis. And once you get in and you do that analysis and you see that you don't have enough depth to cover to get an adequate safety factor, you got to go deeper. And then, oh, geez, we don't have subsurface data at that depth. So we like to recommend erring on this side of caution and going extra deep with borings, because by the time you get your permits to do your borings and you mob your contract and you get out there and the cost to get all this data, it's not that much extra cost to go an extra 20, 30, 40 feet. So just get the data while you're out there. Our rule of thumb is we like to get 20 feet below the conceptual bottom tangent of the HDD. And that's to account for, hey, if we need to go deeper based on the IR analysis. And it's also to account for the tolerance that you give to the contractor to go low of the profile during construction. Because like Mark said, they may steer low and they don't want to be in totally unexpected subsurface conditions. So definitely get geotechnical data below where you think your bottom tangent elevation is going to be. Now, in terms of the locations of the borings relative to the alignment, in an ideal world, we would have them offset from the alignment about 20-25 feet. You do not want them right along the alignment because those geotechnical boreholes are going to serve as a preferential pathway for inadvertent returns of drilling fluid. So we always offset them a little bit. And in addition to that, we always make sure and backfill the geotechnical borings with cement bentonite grout. That also helps to reduce the risk of those boreholes capturing inadvertent returns. In this case here, you can see we've got obviously more offset than 30 feet. Sometimes you're just subject to landowner agreements and access agreements, and you got to get the borings where you get permission to access. So sometimes you have to just get as close as you can. All right. So once we've laid all that out, we're ready to go out in the field and scope it out on the ground. One of the things we're looking for is site access. It was interesting in the environmental compliance talk yesterday. I heard Lee mention that they had a problem where they were 2 weeks, 3 weeks before construction, and the contractor was like, hey, I can't get a certain piece of equipment up this access road you've got. And they had to scramble last minute to permit and site a new access road to get their equipment in. A lot of these projects, the HDD rig sometimes is one of the bigger pieces of equipment. And so, that's one thing that we're always looking at is, what kind of access we have, not only for our geotechnical exploratory boring equipment, but for the actual HDD rig to make sure that they can get into the site and also if there's any kind of improvements that need to be made. A lot of times coming into some of these areas, there's little temporary bridges that have a weight capacity. You may have to put up a temporary structure. So we're looking for that kind of issue. You can see here, this is a site we had once with a maximum load rating on one of our access routes that we needed to be aware of. You wouldn't think at 100,000 pounds that would be an issue. This was for a 36-inch diameter pipeline where our HDD rig was going to be pretty big. And once we get out there, we're looking for other conflicts. Overhead power lines are obviously a very common one that we got to keep an eye out for. Got existing gas pipelines. We're taking a look at basically any kind of obvious utility conflicts. And sometimes you'll see, oh, geez, wow, we've got some potential subsurface obstructions here. We don't know how deep these piles go. And maybe we go back to our desktop study and do some more research, see if we can find out more information on the pilings. Next. And then last but not least, we have to stake our geotechnical borings and call in the locates. Then, so then we start looking at workspace. We want to make sure we have workspace that's adequate for the equipment. Also looking for conflicts. Ideal world here, you got a big 200-foot by 200-foot area, and it's super easy. That's not often the case. A lot of times we're in more of an urban area, and we've got power lines and fire hydrants and access to private drives and all kinds of things we got to try and work around. And so when we're out there, we're fine tuning where our entry and exit points are and the configuration of our workspace while we can get out there and see it.
Take lots of pictures.
Yeah.
You know, and then that can save you having to go back because you need to go back. I remember that.
Yep. Yeah, so this is a typical fairly tight entry workspace area before construction. This is after they've set up, and I'm going to show you a bunch of kind of before and after, so you all have an understanding of what needs to be accommodated for an HDD setup. You know, a lot of these are relatively small rigs for small pipeline in a urban setting. So, you know, here you got the drill rig and pipe rack. You got room for an excavator. This is the drilling fluid recycling system that Mark talked about earlier. But, you know, this represents, you know, pretty close to the minimum footprint for an HDD entry workspace. This is another entry workspace that we worked on. And I mean, this is all we had. We were not able to close this lane of traffic. So this one, I gotta say, was by far the narrowest HDD workspace I've ever worked with. And this is what it looks like with all the equipment set up. So, you know, the thing to keep in mind is if you have a very narrow workspace, then you generally got to make up that space with length. So they're gonna spread out all their equipment over a pretty long stretch. Here it is from another angle. Next. Now, exit workspace, typically you don't need nearly as much space. You know, here's this is basically an exit point here. Next. This is where we come out. You know, in this circumstance, we really don't need much more space than just for an excavator. They don't have a drilling fluid recycling system here. If you don't have room for that, they can have a vac truck and just suck up the drilling fluid that comes out at exit and handle it that way rather than having like a recycling system set up at exit. Next. This is another typical exit space. Again, fairly narrow. Here's our drill pipe coming out of the ground, and really all we need to accommodate is this excavator. Now this is another exit workspace, but here they had the room, so they went ahead and set up a drilling fluid recycling system here, so they didn't have to pump the drilling fluid or truck it back to the entry side. Another example exit workspace. Again, you know, there's the pipe. Not a whole lot of space needed there. Next. And then you got your pullback. And really at the end of the day there, you need room for a side boom or excavators to support the pipe. And that's really about all you need. Any questions about that stuff? So I think we're about an hour in. I think we could take maybe a quick, you know, like 5-10 minute break and come back for the next module on the geotechnical data collection.
I saw that organic farm gave me $500,000.
Yeah.
He's throwing money out there.
The one where I couldn't put my mooring in yet? Yeah.
Somebody asked me.
I'm sure the landowner wouldn't let this on.
That guy was probably, and we paid him $500,000.
Oh, yeah.
He's a genius.
Their crops are always much more valuable.
Mr. Game now.
Well, and they always tell you, after you're in, you somehow like Never be the same, it'll never be the same. Yeah, right. It's like,
Wait, how did we do this? I never talked money because we're staying. Cool dude.
yeah, they're always, yeah, funny. Never walk out.
Yeah, like, what was his cycle?
So they guess all the time?
No, but I mean, he's super smart, but you know, you kind of wonder about him. Genius, yeah, he's smart. He's smart. You gotta have him. Oh, is that?
Yeah, I think your language goes faster.
They were talking about. They had a bike. Yeah. That's what I told
Yeah, that's the way it is. Yeah, absolutely. Yeah, well, because, you know, that's what it's like, I want to put it in, they want to drill it in. It's like, well, you're kind of defeating the purpose that way. Yeah, it gets a little bit sketchy to try to hammer in and on.
Yeah. Yeah, it was like Buck Clean was a long time. We may have, put that far. Just to get, I don't know. Yeah.
All right, so now we're going to talk about the geotechnical data that's got to be collected in order to complete all the analysis for design. First of all, I'm going to go over some of the exploratory drilling equipment. There's a lot of different drill rigs that you can get to access different conditions. There's amphibious rig. You can just do a barge-mounted drill rig. There's a typical truck rig. We do a lot with that. There's all kinds of ATV rigs and track rigs for softer soil conditions. This is a skid-mounted type of rig that typically you'd actually helicopter in, drop into some remote areas. And then I want to go over the sampling and testing that we do once we're out doing the drilling. So this is a split spoon sampler. This is how we sample the soil when we're drilling. Typically, you're going to get a sample about every 5 feet. And this is what's called a disturbed sample. So you can't take this sample into a lab and test its strength as if it were not disturbed or in its in situ state. So instead, as part of collecting that sample, the way that sample is collected is by driving it into the subsurface with a 140-pound hammer falling precisely 30 inches. And so what you do is you drive it in 3 6-inch increments, and you record the amount of blows that it takes to drive each of those 6-inch increments. You pretty much discount the first 6-inch increment, and you add up the second 2 increments, and that is what you call your SPT N blow count. And that value is really the main go-to for geotechnical engineers for estimating the strength of the soil. There's been decades and decades of correlations between blow counts and shear strength for soil. It's the cheapest and easiest way to get the strength of the soil. The limitation is that it correlates very well with granular soils, sandy soils, gravelly soils, but it does not correlate well with fine grain or what we call cohesive soils. And so that can be challenging, and technically you should be trying to estimate your strength of clayey or cohesive soils with other methods. Next. And so this is some examples of other in situ testing methods, meaning you're testing the soil while you're out there drilling in place. And so this is your SPT, and then there's a variety of other methods that are geared more towards getting the undrained strength of finer grained soils in situ, and some other more obscure geotechnical parameters, like the lateral earth pressure coefficient. So, this PMT is a pressure meter test that will give us a value called K naught. It's the lateral earth pressure coefficient, and it's a value that is very useful in doing our hydraulic fracture analysis. And then you've got some dynamic cone penetrometers and dilatometers. These are all very uncommon to actually see being used. I would like to see them used more because it does provide valuable data, but it does cost money. So these are the kinds of tests that we might recommend to an owner-operator for a crossing where the consequences of an IR are really high and they want to really just pull out all the stops and get the absolute best data that can be collected to characterize the conditions. Next. Yeah, the CPT rigs are very they're common and easy to get. The downside of the CPT rigs is that you don't get an actual sample. It basically measures the resistance to penetrate this probe into the ground, and so generally what you have to do then is get a traditional geotechnical boring rig to actually get the samples so you can measure the physical properties and grain size distribution and get a CPT rig. It's not like you can pick one or the other. Next. So this is called a Shelby tube. It's another sampling method. It's not a split spoon. It's just it's a tube that you just push into your clay soils. It's relatively thin walled. It's got a fairly sharp edge. So the idea is that the sample that you would obtain with the Shelby tube is undisturbed. And so therefore you can take that into a laboratory, extract that sample, and then perform strength testing on that material. And that's generally how you're going to get a much more accurate idea of the strength of cohesive soils rather than using the SPT blow counts. This, though, however, is also more expensive. Testing the material in a lab, getting strength testing is more expensive than just relying on SPT blow counts. But again, this is garbage in, garbage out. You know, everybody wants a really accurate model for hydraulic fracture and inadvertent returns. It's only as good as the data you put into it. So it's worthwhile getting good samples, getting good lab test data. Mark? Yeah. Yeah, good timing. So this is rock core sample. So once we hit bedrock, we switch over to coring methods, and we core the rock sample. And as you can see here, we can see these fractures, which in this case, these are all very uniform. So these are generally following bedding planes. This is a sedimentary type of rock. And so we characterize the fracturing of the material and can get a much better idea on the risk of IR. And we'll talk about that a little bit further as well. We generally are sure. We keep them. We test them. I'm going to go into that a little bit on what tests we do on the rock core, and then as a rule of thumb, we like to try to keep them through construction. Some labs, some geotechnical firms will throw them away as soon as they've completed their testing. But the problem is if during construction, the contractor makes a change of conditions claim. We don't have any proof of what the material was that was encountered to show that it absolutely does represent what was shown on the logs and what they were provided in their bid documents. So we generally try to keep the samples until construction's complete and there are no change of conditions claims for subsurface conditions. Okay, so this just shows some of the data, the field data that we collect on the rock core. So we make an estimation based on these field identification characteristics of how hard the rock is and the unconfined compressive strength. That'll actually be tested in the lab. That's the unconfined compressive strength, one of the most important parameters for the rock to provide for the contractor, because they're going to select their tooling and their bit accordingly. And then down here we have our discontinuity spacing, and then the most widely accepted way of expressing how fractured the rock is what's called the RQD, or rock quality designation. And it's really a numerical expression of how fractured it is. And that really comes into play with the risk of inadvertent returns, but also can really potentially render an HDD infeasible. If you've got very poor quality rock, it's fairly hard and very fractured, very closely fractured, it's going to kind of behave like a gravel, and you're going to struggle maintaining hole stability. So these are all very important parameters to collect for the rock core. Now, this is an interesting picture. A lot of times we have a hard time getting drillers to core in non-ideal conditions, and this is actually a semi-cemented gravel. It's probably a glacial till that is all rounded gravels that we were actually able to extract a core from. Because this kind of stuff here, you aren't going to drive a sampler into that. So you would with the SPT test, be pounding that sampler on here and just getting refusal with the sampler, and you'd be getting no data. So this was important that we were actually able to extract core on this and see what we were dealing with, because these kind of conditions right here, very challenging for HDD.
Till, and thank you, I can hear myself. We cored glacial till, and we actually cored through like an 8-foot thick boulder. So we were in soil, went through an 8-foot thick boulder, and then came out and we're back in soil again. Because you're in glacial conditions, you can run into these giant boulders that are buried, and it was good information to have.
Yeah. Okay, next. All right, so we want to talk about the laboratory testing program that we would typically recommend. So we want a good idea on the grain size distribution. That's important for a lot of the aspects of HDD design, from gravel size, material, fine gravels, sands, down to silts and clay size particles. This is how the grain size distributions are typically plotted from laboratory testing. And it shows your percent passing by weight of these various sized particles. And one of the big important factors here is your percentage of gravel. The greater percentage of gravel that you have, the greater the risk there is to the HDD operation, up to and including failure to install an HDD. Gravels are really the killer for HDDs. And the problem is it's really twofold. The gravel class are heavy enough that they're going to collapse. That drilling fluid is not able to hold that hole and support the hole when you've got relatively large gravel class. And so you're going to have a hard time keeping a hole open. And, talking about that pneumatic hammer, you may find your contractor trying to hammer the pipe into a hole that's half collapsed with gravel class. And even if the problem is, even if it can hold a hole okay, you still got to transport the cuttings out, and those gravel class are too heavy to be suspended in the drilling fluid, and they will fall out of suspension. And so you're then looking at having to come up with mechanical methods to pull out the gravel, and that can be pretty challenging. Next. Atterberg limits, it's a fancy word and method for determining how clayey your material is. Next. So you plot the results of your Atterberg limits test on a plot that looks like this. These symbols stand, the CH right here stands for fat clay. It's that, it's like pottery clay. It's, really, really clay stuff. Then you've got lean clay, and then you got clay silt mix. ML is silt, MH is elastic silt. And this is a very important parameter as well for HDD consideration, because as we'll talk about later in risks and considerations, it tends to be that you have more problems with the more plastic, sticky type material, both in IR and in other ways that are affected during the operation. Next. And then we get into some various strength testing. One of the more standard ones is an unconfined compressive strength test, and you can do this in soil and rock. This essentially gives you your cohesion of your material. Next. Triaxial shear strength testing, getting back to those Shelby tube samples I was talking about and getting undisturbed samples. Again, this is substantially more expensive than just relying on correlations from blow counts. But as I say, those blow counts just don't correlate well for the cohesive strength of clay. And it's those clay soils that are generally your bad actors for inadvertent returns. So it's worth one of these tests, these can be upwards of $1,000 or more for one test. But this is strength data that's much more reliable than just correlations from your SPT blow counts. So we would typically include at least one triaxial shear strength test for fine-grained clay soils on HDD projects, particularly where IR is a big concern. Next. We do consolidation tests, which is an odd thing. It's pretty rare for most people to see a consolidation test for an HDD project. Generally, people do consolidation tests for big foundation settlement and determine how much some big heavy structure is going to cause settlement. As it turns out, a consolidation test can give you this parameter K naught, coefficient of lateral earth pressure. The only other way to get that parameter is to do one of those other in situ tests I talked about with the pressure meter testing or dilatometer testing, which is very expensive. It's difficult. So this is a little bit of a cheaper way to try to get this parameter. Mark's going to talk about this a little bit more in the hydraulic fracture analysis section. Over the last several years, this has become a little bit more of a focus in IR analysis. It used to be really discounted, and over the last several years, a lot of the community is recognizing it's a pretty darn important factor for accurately characterizing the risk. The Army Corps of Engineers just came out with a bulletin, right? Some revised guidelines, Mark, that clarified that K naught should be considered in the hydraulic fracture analysis, and so that's something we're trying to do. All right, so once we've done all of this, we've got all our data, we put it all together and go, okay, do we have any deal killers here? Any red flags? Do we still have a viable HDD? And provided that you have not encountered a whole crap load of gravel, you probably still have a viable HDD. That's really the deal killer. And if you've managed to avoid a bunch of gravel, then you at least have still a project here for an HDD. Next. The next thing we look at is soft clay. Yeah, it can be problematic in terms of being more vulnerable to inadvertent returns, not only because of the nature of the material and its shear strength, but also because the way it behaves during drilling. So here's a typical IR here, drilling in clay. Next. So one of the other things, not only is it generally weaker than like sandy soils, and so more vulnerable for IR because of that, one of the other big problems is it's sticky and it just balls up around your tooling and it clogs off the hole. I mean, Mark will get into it in the hydraulic fracture analysis section, but you may have seen, say, hey, we've got a safety factor of 2. or a safety factor of 3 against IR. Well, that safety factor assumes you have a fully open hole and you've got full drilling fluid returns to entry. It really assumes fairly ideal conditions. As soon as you have clay balling up and plugging off your hole, all that goes out the window. Your pressures go up and those safety factors start getting eaten into. So really, in my opinion, this is the biggest problem with clay is keeping those returns and keeping the hole open.
Their big side.
Yeah, they come off in big ribbons as they cut it, and it's kind of like the gravel, right? Because it doesn't get minced up into nice little, like sand. It comes off in big chunks and ribbons, and it either sticks to your tooling and your drill pipe, or it actually falls out of suspension and starts accumulating in the bottom of the hole.
There's some kind of charge. Right? That's what they told me.
What's that?
Well, there's a charge on the, they had a charge on the back lane.
Well, yeah, I mean, there's a chemical bond. That's what gives clay cohesion in general. But yeah, I mean, it's just as simple as the stuff stays in big chunks and it's heavy and it just accumulates and it's hard to break up. They can use surfactants. There's a lot of different drilling fluid additives that they can use to try and break it up, but it's always a challenge. And then the other thing that we also consider is groundwater. It's interesting during the environmental compliance talk yesterday. It sounded like Dominion's had a few challenges recently with capturing groundwater. And the challenge with groundwater is that if it starts uncontrollably coming out of your entry or exit point, you got to pretty quickly start figuring out how to contain that stuff and pump it and prevent it from going somewhere that it shouldn't. So that's definitely a consideration we look at in the feasibility phase. All right, so with that, I'm going to hand it back over to Mark, and he's going to go over some of the details on the engineering and analysis side of this. Yeah. Yeah, all the time the contractors will commonly use that, particularly if there's an IR. Really, that's a lot of times one of the best hopes we have is to try and seal that off with some lost circulation material and hope to keep that drilling fluid from continuing to go where it's not supposed to. I'll be honest, it's a crapshoot on whether that actually works. A lot of times it doesn't, and then you just kind of have to isolate that area where it's going and pump it back to your drilling fluid recycling system or your entry pit. Yeah. How many geotechnical borings? Yes, like I was saying earlier, I mean, we do kind of have a rule of thumb in that we somewhere around 1 every 500 lineal feet or so, but I hate to even say that because it's so dependent on each site and the conditions and the complexity of the geology. Yeah, if you go all across your HDD across 4 different geologic units of differing material, you're going to need more borings to characterize it. And a lot of times, I didn't mention this before, you'll start off with a plan, an exploratory plan. You may have 3 borings to a certain depth. The biggest problem is if you go out there just in, hey, I'm going to complete this program blindly and head on back to the shop, you're going to have a problem. You know, we always have somebody out there that really understands HDD. They understand when they're in conditions that are not conducive to HDD. And it may be, you know what, by the time we're at let's say we planned our borings to 70 feet, and at 70 feet, we're in really crappy material, we're going to maybe keep looking. On the other hand, you may have one boring, you've got a certain kind of material, and then the next boring, you have something completely different. And you got a river in the middle. Okay, well, what are the conditions at my river? You know, if you've got completely different material between two different borings, you may have to make a decision to add another boring between those two to understand better where that transition occurs. And so at that point, we'd make a phone call to our client and explain the situation and recommend that we get another boring. So it's highly variable. But, you know, I think if you're looking at much less than one every 500-600 feet, you know, it's borderline. Any other questions before I hand it over to Mark? All right.
All right, so now we're going to kind of get into some more of the technical stuff, some of the things to think about during design, some of the things that would be beneficial to think about, and then also get into talking about some of the stress calculations. We're not going to get too crazy into the math, but we'll also talk about how to like fracture analyses. We'll show you some of the equations that are typically used, and basically also to describe some of the pitfalls. Trevor mentioned some of the things already, so it's kind of pre-primed you for some of the stuff that I'll talk about. So go ahead. So design considerations. So, you know, if you got a drill that's out in the middle of a cornfield or something, you know, in an undeveloped area, you know, you can pretty much put your workspaces, put your entry and exit points wherever you really need to. But, you know, you've seen some pictures today where we're in pretty heavily congested areas, tight corridors, lack of workspace, you know, with a lot of existing utilities. And so you can see here, you know, we've got overhead electric line, we've got a telephone line. I don't know if that's above or below ground. We've got a water valve, fire hydrant. We got a water line here, and then we've got this gas line back here. So when you're thinking about where you're putting your entry and exit points, you need pretty good data on you need your utilities located. You know, you could spend a lot of time trying to figure out where the best place to put the entry point is. But if you haven't identified something in the early site investigation, you know, you may end up having to do something on the fly during construction. You know, the contractor calls in to locate. It's like, oh, guess what? We found something we didn't know was there. Now we have to modify some things, which, you know, could be a problem. Maybe not often, but it could be a bigger problem. So when you're thinking about like where your entry point's going to be, well, where's your rig going to sit relative to that? How long you figure the rig's going to be? Is the anchoring system for the rig going to be on top of an existing utility? You know, there's some things to think about. You know, some pipeline owners don't want you putting a drill rig on top of their utility. You know, we've had issues where, you know, the rig kind of needed to sit where there was a water line, but the local municipality didn't want us putting a drill rig on top of their water line. So all things to think about. Maybe if it's a small rig, it's not a problem. Maybe if it's a big rig, it is a problem. So just things to keep in your mind when you're laying these things out. So again, if you're in a cornfield somewhere, you probably don't need to do an extensive, you know, utility locate, but in these congested areas, you definitely need to be thinking about, you know, trying to find everything you possibly can in these areas so you can lay them out ahead of time. And then also think about, in order to do your tie-in, you're going to have to dig this back, right? So wherever this entry point is, your actual tie-in to the conventional lay section is going to be back here somewhere. So you got to figure out where that's going to be. How hard is it going to be to dig this back, dig it down deep enough? You know, what other structures might there be? Because if you're going to have to dig an 8-foot deep excavation, let's say, you may have to slope that or use trench boxes. All things to consider when you're laying out these endpoints. So the other thing to think about too is environmental or sensitive features. We've already talked about this lady over here. She asked about where do hydraulic fracture invert returns typically occur? Well, it's near entry and exit. So, one thing you probably want to do is make sure you provide some space from the ends of your drill to any sort of sensitive feature. 50 feet, I would say, would be a minimum. 75 feet's better. Because there's a good chance you're going to see some frac outs where your drill profile is still shallow. So where are your wetlands? Get your wetlands delineated. And actually on this drawing in the profile, we've indicated kind of where those sensitive features are in the profile so that once we have geotechnical data, we can kind of see. Here it's a little sparse, and I don't know, Trevor, if you have an answer. I mean, it would be good to get a boring in here, but sometimes, access into some of these areas and permitting a boring in a wetland area can be difficult.
Yeah.
You're turned off again.
Yeah, on that one, we would have had to cross both of those wetlands and disturb them to get a boring there in the middle. The other thing I wanted to point out is that we want to have typically 50 to 100 feet in front of our entry and exit points to account for the higher risk of the IR. And we always make that part of the entry and exit workspace so that the project team is then permitting those areas for disturbance. So even though they would be IRs technically in those workspaces because it's not going to the entry or exit pits. If it's been permitted for disturbance, it really shouldn't be a reportable or any major issue because it has been permitted for disturbance.
Well said. Next slide. So we talked a little bit about entry and exit. Somebody have a question? Okay. We talked a little bit about entry and exit angles. We had a slide earlier that said they're typically 8 to 12 degrees. That's just kind of rule of thumb. There's no hard and fast rule. I will say that some of the smaller drill rigs tend to be a little bit more flexible on the angles that they can achieve. The big drill rigs for large crossings, they'll only go down to about 10 degrees, is about as low as they'll get. So if you need a lower entry angle, then you're going to have to dig the back of the rig down. But remember how we talked about there's a higher risk of invert returns where the drill profile is shallow? If you're entering the ground at a very shallow angle, that drill profile is going to be shallow for a longer distance. So that range over which you have a high risk of invert returns is going to be over a longer distance. So if you can enter at a steeper angle, you get deeper faster, you're kind of less prone to have those hydraulic fracture events or invert return events, far away from the entry and exit points. I mean, you can go steeper than 16 degrees for your entry angle, but the other thing to consider is, you're going to have people working on the rig, and as it gets steeper, it becomes kind of more of a safety concern, particularly on a bigger rig where you got people actually loading drill pipe onto and off of the rig. They're having a wireline connection. They're having to make wireline connections. So the steeper you get, it gets a little less. There's kind of more safety issues there. And then the exit angle, we talked a little bit about that. I would say 8 to 10 degrees is pretty typical. The bigger the pipe gets, we showed that overbend earlier. Larger diameter of the pipe, the larger that radius of that breakover is going to need to be. So that's going to make that overbend, the top of that overbend, higher and higher and higher. The larger your pipe gets, the higher that overbend is going to get. So for larger diameter pipes, you want to reduce that angle as much as you can and still be reasonable. Like I showed earlier, we had that picture where they dug that little tail ditch, right? That allowed them to keep that overbend lower to the ground. So it's kind of one trick you can use or think about doing during construction to kind of reduce the height of that overbend. So.
Yeah, I was just going to comment on the smaller diameter pipes, say like 12-inch and less. I mean, we're commonly looking at 14 degrees, sometimes 16 degrees for entry and exit, just as Mark said, just to try to reduce the distance that we have a high risk of IR. And with that small pipe, those angles just aren't typically a problem.
Okay, so we're going to talk about design radius. This picture will come back again later. I'll explain it. But so when we're designing a drill, obviously it's got some curves in it, right? So typically, simple drill, it's got 2 vertical curves, 3 straight tangent sections, pretty simple. Now you can get more complicated than that, but there's no need to get more complicated. It's kind of the KISS rule, keep simple, stupid. Don't get any more complicated than it needs to be, because the more complex the geometry gets, the harder it gets to drill, the more potential for problems during the construction process. So, but basically you got vertical and horizontal radius curvature. So if you need to make a change in the alignment, you can put some horizontal curvature in it. Obviously, you've got your vertical curves. Where you have overlapping horizontal and vertical curvature, you're going to have a compound radius or combined curvature. And so if you have a 1,000-foot horizontal curve radius and a 1,000-foot vertical curve radius, I don't know what the number is. It's probably around 700 feet or something. So combined, that's really in 3 dimensions, that's about a 700-foot radius curve. So if you're going to have combined curvature, you need to take that into consideration later in your calculations. So, and then one of the things that we don't see on some people's drawings when they produce a drill design is a minimum allowable 3-joint radius. So when we were talking about drilling the pilot hole, and we'll talk more about this later, you know, that pilot hole is drilled on a curve. And one of the things we look at during construction is we look at what that radius of curvature is that they actually are drilling. So you may design it at a 2,000-foot radius of curvature, but the driller's never going to drill it at exactly 2,000-foot radius. And so, how I said before, you know, you want to allow the profile should be designed such that it allows them to catch back up, right? So they need to actually have the ability to drill a tighter curve than the design radius. And so one of the things that should be on a drawing is a specification that says it's designed to a 2,000-foot radius, but you're allowed to drill down to, let's say, 1,500. That's the minimum allowable, right? So because the tighter the curve radius gets, the harder it's going to be to pull the pipe through there, the higher the stresses are going to be on the pipe, and ultimately, during operation, the stresses on the pipe are going to be higher as well because it's at a tighter radius. So.
Yeah, Mark, I was just going to add to that. You know, there's a lot of times we'll do a third-party review on designs, and it's pretty common that you won't even see a spec for a 3-joint minimum radius. And at that point, then the contractor can do it as tight as they want. And so all of the design and effort you put into making sure that your radius is meeting the requirements of operational stresses, that goes out the window because the contractors, I mean, their path looks like a drunk driver. I mean, this steering is not an exact science. They're all over the place trying to track to the alignment, and they're making corrections. And a lot of times, you know, they'll maybe make a correction that's too tight, and that's going to give you problems not only with operational stresses, but for actually pulling in the pipe. And so it's really important to have a specified minimum 3-joint radius and hold the contractor to that.
Yeah, or the alternate is instead of not having a minimum radius, someone just says, well, it says 2,000 on the drawing, you have to drill it to 2,000, which isn't possible. So, next one. So Trevor kind of covered this a little bit earlier, talking about different types of materials and risks. This is a very just obviously simple chart. So we're talking about construction risk versus soil type. We'll talk a little bit about rock and some of the, well, I guess Trevor already did talk about rock in some ways, but we'll talk about that too from a hydraulic fracture, invert return standpoint a little bit. But really there's 4 things when it comes to soils. You've got steerability, hole stability, hole cleaning, you know, how well you're going to be able to get those cuttings out of the hole, and hydraulic fracture / invert returns risk. So there's 4 things, you know, when it comes to soils, they're kind of the 4 key things to think about. So with sands, you can steer pretty good in them. Not really a hole stability problem, you know, as long as you got your drilling fluid properties squared away. They're good against hydraulic fracture because they're strong, so you have a higher resistance to hydraulic fracture, and the cuttings come out really well. You know, sand particles are very easily suspended in drilling fluid. It's easy to get them out. It's easy to keep the hole clean, assuming your drilling fluid properties are good. Then as you move to silt, still steerable. Still, you can get the cuttings out of the hole. They're not real sticky like some of those fat clays. So the hole clean tends to be pretty good. On the inadvertent return side, not as good as sand. They tend to be weaker, higher risk of inadvertent returns in silts. And but from a hole stability, it's fine. Clay, good steerability, hydraulic fracture resistance, low. Hole cleaning ability or troubles with cleaning the cuttings out, not great, but stability is good. And then gravel, basically steerability is bad. Inadvertent returns can be bad. Steerability, inadvertent returns. Inadvertent returns, let's see, hole collapse, bad. And steerability, bad. All four bad. So, I mean, it can kind of depend because gravel's not just necessarily just bowling balls. You know, it could have some sand and silt mixed in with it. So maybe it's not always extremely bad, but it's not good.
You mentioned you're going to talk a little bit more about rock. Is there a place to put that on that graph?
Rock, I guess.
Risk.
From rock, it's hole stability. You know, if you have, like Trevor said, if you have really highly fractured rock, it can kind of act like a gravel, or it just won't hold itself open. And then you also have those fractures or a pathway for drilling fluid to escape. And where they go, I don't know. Sometimes they can surface a long ways away. So.
Yeah, and we'll touch on it a little bit more in the hydraulic fracture section, but the toughest thing about it is you can't model it like you do. If you do a hydraulic fracture analysis in soil, we have that modeling done pretty well if you get good geotechnical data to populate it with. Rock is just random, unfortunately, and that's a challenge for our clients, the owner operators. You know, they want to do everything they can to prevent releases. They want to have predictability. They don't want to have problems. And all the best we can do is really, you know, say, hey, based on our judgment, you know, our gut feel for this rock based on its fracturing is whether it's, you know, low, moderate, or high risk. But that's the worst part about it. It's generally unpredictable. But overall, most types of bedrock, you're going to be in pretty good shape and have a relatively low risk of having problems. But we'll talk about some nuances on what kind of bedrock is more problematic here in a little bit.
I work out in the Charlotte area, and I saw on one of the earlier slides, you kind of had that geographic analysis, and it looked like there was a small strip that kind of cut through Charlotte. And I'm just kind of curious.
Are you talking about that geologic map?
Yeah.
I don't.
Yeah, so through that area, I mean, almost all of the bedrock from Charlotte west it's all some type of form of what we call gneiss. It's like a metamorphosed granite. That stuff tends to be pretty good. I don't know that I've actually experienced or seen an IR from within that kind of rock.
It's usually pretty good.
Yeah, so.
Yeah.
Oh, it's harder than, it's going to cost you a bundle on a per foot basis. But it's pretty predictable for IR risk. It's the sedimentary rock, the softer sedimentary rock that tends to be a bigger problem.
Thanks.
So this is just
Go ahead.
the targeted design.
Oh, okay. Sorry. So once you have your geotech, then you could put the borings on the profile like we've shown here. So this gives you a pretty good idea of what sections of this drill profile will be drilled through. So you kind of have an idea, you know, maybe there's a zone where in this particular case it was rock, this crossing, primarily rock. You'll have a better idea of, okay, well, this zone might apparently had more fractures in it. So we may have some hole stability issues here, you know, maybe not expecting disaster, but, you know, it'd be a place to look for where maybe the reaming doesn't go very smoothly. Maybe the torque values are erratic, you know, so you kind of watch some of the values during the actual construction process to see, if you might be hitting some more fractured rock and if that might later be a problem. So it kind of gives you some ideas of where to look, things to look for where you might have some potential problems. Go ahead.
Yeah, and I was going to follow up on that. I can't tell you how many times I've seen folks that are kind of decouple the geotechnical data from the HDD design. They kind of see the geotechnical data as something that's needed for the contractors. So they develop a profile, they get geotechnical data, they slap it on the profile, and they send it to bid. That's really skipping a big step. I mean, you can really reduce your risk and improve your chances of success by tweaking that profile and tailoring it specifically to the results of those geotechnical borings to absolutely reduce the risk the best you can with what you know. So it's important to take that step and do the tweaking as needed.
And that's why it's nice to couple engineering.
Right. Yeah. We're big proponents of that. We much prefer being in charge of the geotechnical program when we're responsible for doing the HDD design, because it really is an iterative process.
You mentioned it before. How much deeper do you go on the bore samples versus the profile?
20 feet below the bottom tangent.
Actually, I would add one thing. During the drilling, it's always good for the person who's out there logging the borings and collecting the samples to communicate back to the office so that, before you end a boring, they can call the office, say, okay, we're gonna complete this boring, we're gonna terminate it here, here's what we're in. And it could be like, well, maybe we should go another 10 feet. We're already there. This material is not good. We're starting to get into something better. Let's go another 10 feet, 15 feet. If we can confirm that we're in some better material, well, then that could be useful later on down the road.
Is there a point where your flow count is just so high that it's like you can't go any deeper?
Well, you could drill through it, but sampling then becomes an issue, and then you might have to then switch over to like rock coring. Okay, so let's talk about installation loads and stresses. So one of the things that should be done during the design phase is to estimate what your pull forces are going to be. This gives a contractor a bit of an idea. I mean, they have experience. Contractors do this every day, so they kind of understand certain length of crossing, certain diameter pipe. I'm going to need about this big a rig. But we can estimate this, and these are estimates. When we do these calculations, we're assuming the perfect hole geometry, the hole's perfectly a cylinder, which is not the case. So you have to take some of this with a little, not grain of salt, but realize that things may go differently during construction. So one of the things that's important to do, and this is for small diameter pipe that you're not going to add any water to for buoyancy control. Larger diameter pipes are going to be very buoyant when you try to pull them, so you need to add water. Reduces that buoyant weight, reduces the pull forces by a lot. And we'll show kind of an example of that. But so we look at different drilling fluid weights, and it says buoyancy condition. We're saying empty, so we're not adding any water to it. So you can see that what the effective weight of the pipe is. So these negative values indicate that it's buoyant. So in order to get it to sink, you'd have to put 42 pounds per foot on it. So it's pretty buoyant and wants to float pretty hard. And then pullback force. And you can see that even with just these are 9.5 and 12 pounds. That's a fair range of drilling fluid weights, typical. It can be higher, not much lower, but you can see that even just a few pounds per gallon of drilling fluid weight equates to about 6,000 pounds of pull force. So on bigger pipes, this effect gets a lot bigger. So next slide. So this is for a larger diameter. So in a larger diameter crossing, I would say 24 inches and up, typically, you're going to add water to the pipe to reduce buoyancy. I've seen it used on smaller diameter installations for certain reasons, but typically 1,000 feet of 24 inch, they probably won't. If it's 5,000 feet of 24 inch, they probably will add water. Just kind of depends on the situation. It's just more work. So if they can get away with installing a pipe without having to do it, the contractor would rather not have to. So again, same range of drilling fluid weights, 9.5, 12, but here we compare empty condition versus full. So What is it with no water in it? What is it assuming we fill the pipe with water? And of course, that's kind of an idealization because when they do add water, they don't fill the entire thing all the way to the top, you know? So there's always going to be a little bit of discrepancy there. But you can see that between 9.5 pound, if you had 9.5 pound drilling fluid downhole, empty and full, not a huge difference, you know, 9,000 pounds, 11,000 pounds. 12 pound drilling fluid, you can see a pretty significant difference there. So what is that, 48,000 pounds between no water and adding water to the pipe. So it's good to understand what that is. And then also you can kind of calculate too what the safe pull force for that particular pipe might be. So you can see kind of how close your pull forces are getting to what would be considered a safe pull force. And then here we did a case just for neutral buoyancy. You know, if you could get that pipe neutrally buoyant, what might the pull force be? So you can see how much it reduces it if you could get it perfectly neutrally buoyant, which realistically you can't. So it just gives you an idea of an ideal solution. Next. Operating stresses. So once this pipe is installed, it's tied in, it's operating. You know, we know the pipe specifications, we know the operating pressure. We need to calculate what the bending stress in the pipe is. We need to calculate the hoop stress on the pipe, the longitudinal stress. Hoop stress creates the longitudinal stress. Any thermal stresses on the pipe, the net longitudinal stress, and then the maximum shear stress and combined biaxial stress. So we have to check all these things. These are in the ASME B31.8, B31.4. We have to abide by all that stuff to make sure that during operations those things are not violated.
You know, I was going to mention, I was talking about that 3-joint radius before. Got to make sure that these calculations are based on the specified 3-joint minimum radius, not the design radius. Because it's that 3-joint as-built radius, that minimum radius, that controls the design here, not the vertical or horizontal radius that you have in your design drawings.
And we're going to assume that if you give them a minimum, they're going to hit it. So good point. Yeah, as noted at the bottom. So go ahead. And then for plastic pipe, we also look at, you know, plastic pipes, not as strong as steel pipes, more prone to collapse. So we have to look at the wall stress and the collapse factor of safety over there in the last two columns. And because plastic pipe, the elastic modulus of plastic pipe reduces over time. From when it's brand new to when it's been in service for a long time, the elastic modulus goes down. So what happens is the potential for that pipe to potentially collapse or have a failure increases. So we look at different cases. So we look at when the pipe's tied in, whether the pipe is empty or full, because empty condition, there's nothing in it. Full condition, you actually have some internal pressure here, and that internal pressure helps counteract the external pressure. So you can see that from a wall stress factor of safety and a collapse factor of safety, it gives you a better factor of safety. And then we look at operating conditions. So let's say maybe when the pipe's under pressure, we look at the same thing. And then under maintenance conditions, let's say it's not in operation, we look at it depressurized and empty and depressurized and full. So we kind of look, and you can see that from the time it's tied in, let's say it's empty. Let's say it's a natural gas line, so there's no fluid in it. Well, tie in, there's factor safety of 6.5, but because of the modulus of the plastic reduces over time, you know, we actually use a modulus at maintenance case of 50 years. So we reduce the modulus down to a 50-year modulus, and you can see that the factor of safety goes down to, a 3.0 from a 6.3. So we have to look at those things to make sure the pipe is efficiently designed throughout its design life. So we talked some about hydraulic fracture, some of the things we need to know. And so we've got the next slide. I'll show kind of some of the things we need to know. But essentially, it's the formation limit pressure, the maximum pressure that the formation can take, relative to our anticipated drilling fluid pressure. So let's say the formation could take 100 psi. If we're calculating the drilling fluid pressure should be around 50 psi, you've got a 2.0 factor of safety. That's pretty good. So what do we need to know? So for the formation limit pressure, we need to know some of the soil properties. Sorry, Trevor talked about those earlier, the shear strength, we need to know unit weight, shear modulus, Poisson ratio, elastic modulus, coefficient or lateral earth pressure, and that K. We'll talk about that more because there was, let's say people did hydraulic fracture calculations for several years before they realized they needed to take this into consideration. So we'll talk about that a little bit. We'll need to know groundwater elevation because that impacts the stresses in the ground at depth. And then annular drilling fluid pressure, how do we calculate that? You know, and this is downhole pressure. This is not at the pump, but this is from the pressure tool that we saw earlier, downhole, right behind the drill bit. We need to know the bit diameter, or the hole diameter. We need to know the drill pipe diameter. We also need to know the drilling fluid weight, because there's hydrostatic pressure, you know, due to the drilling fluid. And we need to know the drilling fluid rheology, namely the plastic viscosity and the yield point of the drilling fluid. One thing to consider here is when you're designing one of these things and you're doing these analyses, you don't know for certain what these are going to be. I don't know. You know, the driller may decide he wants to use an 8-inch drill bit, where another one wants to use a 7-inch drill bit. Well, that's going to affect your drilling fluid pressures. So all you can do is you kind of give it a best guess based on experience, what you've seen in the past, on what these parameters are likely to be. And then if need be, you can update those prior to construction. You know, contractor does a drill plan. They say, okay, here's what tooling we're going to use. You could rerun the analysis pretty quickly. Say, okay, now we've kind of got a little bit better idea. We've honed in a little bit closer on what the pressures might actually be. And actually, if you have good clean hole, you know, you're keeping the cuttings out of the hole, you can run pretty close to this, you know, these calculated pressures. So these are equations over here. They're fun. We won't get too far into those, but there's really two mechanisms of failure. There's a shear failure. Some people call it blowout, where you actually exceed the shear strength and overburden pressure of the formation. And then you have a tensile failure. So this is kind of the cross section of a hole right here. And what you're seeing is once the pressure in the hole gets high enough, it exceeds the pressure holding the formation together, and you get a tensile fracture at the top. And it just essentially just splits the crown of the hole. And as you can imagine, once something like this starts, it's not hard for this thing to just keep going straight to the surface. Unless you have some layer of material above you that is much stronger that could stop that continued flow to the surface, the continued fracture to the surface. So as Trevor pointed out earlier, there's this K0 value. It's one of the things he talked about in lab testing, one of the things that's valuable to know. The Delft equation, for a long time, people assumed that it was a hydrostatic stress state. Basically, your vertical stresses in this plane were the same as the horizontal stresses in this plane, which in reality in soil, that's not true. In most cases, your vertical stresses are higher than lateral stresses. That's where that K0 comes in right here. So typically, this K0 is just a coefficient. So if you have a P0 of, let's say, 100 pounds per square inch, and your K0 is 0.5, well, then your lateral earth pressure is 50 psi. It's pretty simple. But as you can see, that horizontal pressure, if it's less than, you know, if it's 50 psi, really all you got to do to overcome the strength here is 50 psi plus the tensile strength of the material, and you can fracture it. So it doesn't take a lot to create this tensile fracture. And here are, well, these upper two equations are called the Queen's equation. They were developed at Queen's College in Canada. And you can see here that this equation on top is for K0 of less than 1, and then have a different equation for K0 less than 1. That's why if you're going to use this equation, actually if you can use either of these equations, it's important. But something to think about. You need to know this K0 before you know which of these two equations you need to use. Now this equation down here this is called the Delft equation. It's been around. It's probably the most widely used equation. And for a long time, people did not take into account, as I said, this K-naught variable, which actually should go into this P prime F. So the Corps of Engineers guidelines that Trevor mentioned a little bit ago, they've since required that this be considered, this K-naught be considered into this P prime F, because a lot of people weren't doing that. And so what that ended up doing, it gave you very unconservative results. It would give you huge formation limit pressures in sands that were just unrealistic. It's because people weren't applying this K-naught value, which by applying that for sands, it's in the 0.5 range. For a lot of sands, this K-naught's gonna be about a 0.5. So applying a 0.5 to this and running this giant equation is gonna reduce your formation limit pressure by a lot, and actually tend to be, I think, a lot closer to reality using a K-naught. So K-naught's important. As Trevor said, there's ways in the lab to determine that, or at least estimate it close enough for what we're doing. So anyway, I'm going to talk a little bit about drain versus undrained. And, you know, a lot of these slides I could probably talk about for an hour or so, but we're not going to do that. So let's consider soils as sands, and then fine-grained soils that are silted clays, right? Well, typically in undrained condition, a saturated soil, a sand, if you apply a load to a sand, a saturated sand, that sand's going to want to try to compress somewhat. Because it's porous, the water can just go away, you know. In a clay that has very low permeability and it's saturated, you apply a load to it, it's like a tuna can with the lid still on it. You can't squeeze the water out, right? You cut the lid off, you can squeeze the lid and drain the water. Drain versus undrained. Well, when you're drilling in clays, you really have an undrained scenario. You know, that pressure from the drilling fluid being placed on the formation, that pressure has, the water in that formation has nowhere to go. It can't dissipate fast enough. It can't drain away. In a sand, when the drilling fluid pressure hits that formation, the water in the formation can just kind of dissipate. The pressure just dissipates. And so typically, this is how the Delft equation needs to get boiled down. And again, there's a lot to this, but for silt and clays, you would put in a zero friction angle here, because in undrained conditions, a clay has a zero friction angle. And so basically, it needs to boil down to this, with zero friction angle. So clays, silts, anything fine-grained, anything in low permeability, saturated conditions, it's a pretty simple equation. Gets rid of a lot of stuff. In sands, you can use a friction angle. It's a drained case. And for a lot of years, people had issues because if you plug this thing into a spreadsheet, this equation, you program a spreadsheet with this equation, and you try to plug in zero for this friction angle, this phi value here, it can't calculate it, because this cotangent of zero is infinity. So it blows up. Excel doesn't know what to do. But if you reduce the equation down, you can reduce this down just by looking at the terms of it. It goes to that. You can easily calculate it. So what people would do is they would put a small friction angle, 0.1 degree, 1 degree, whatever. Even doing that gives you unconservative results. It gives you a way higher pressure than it should. So
yeah, and I would say that, you know, whenever you have an unexpected inadvertent return where you've calculated, or somebody has calculated, say, a safety factor of 2 or 3, a lot of times when you look at it, it's because perhaps drained strength parameters were used instead of undrained strength parameters. Because I know this is all, you know, nobody likes to see equations at, you know, 2:45 in the afternoon. But the bottom line here is, if you have undrained conditions with a phi of 0, you end up with a much lower safety factor predicted in your model. So it makes a huge difference on whether or not you consider your conditions, your soil conditions, drained or undrained. And so that's where the judgment of the geotechnical or HDD designer can come into play and make a huge difference on the results of your model and what your safety factor is.
yeah, because for a clay, under drain conditions, you could maybe use a 20-degree friction angle in drain conditions. But for undrained conditions, we have rapid loading, pore pressures can't dissipate, you need to use a 0 friction angle. And some people don't, but anyway. We talked about hydraulic fracture and rock. Well, Trevor showed some rock core samples earlier, and they looked a lot better than this. But you can see here, you've got this highly fractured zone here. You've got all these different bedding planes. You got some fractured stuff here. So in rock, you don't need to fracture the formation. It's already fractured. Basically, all you need to do is overcome whatever overburden stress is in the formation. So if it 50 feet deep, the overburden pressure is, let's say, 50 psi. If you can overcome 50 psi of drilling fluid pressure, you're likely going to start losing fluid into these existing bedding planes, fractures. And, you know, there's been instances where the contractor could be losing drilling fluid, and they're losing it slow enough they don't even know it. You know, they're losing maybe 10 gallons a minute, but they're pumping 200 gallons a minute downhole. So it's not really that noticeable until a quarter mile away, it comes up in somebody's yard, comes up in a stream. It's happened, it's come up. We've seen invert returns further than a mile from the site. So not only is this a problem in fractured rock, like sedimentary rock, softer sedimentary rock, but also karst. So limestone geology, like in Florida, in Missouri, there's locations in Georgia where you've got highly weathered limestone that's got a lot of voids in it, a lot of interconnected voids. It's very permeable. And basically, it's like a sponge. It's like trying to pump fluid into a sponge. It just goes into it, right? So it's not only sedimentary rocks, it's karst geology. We have a client with a project in Texas. There's some limestone there. They started drilling, got into the limestone, drilling fluid disappeared. They couldn't keep the returns flowing. And a couple miles away, guy ended up having drilling fluid coming up in his well. There's now a lawsuit. So it's important to do your homework ahead of time. If you have limestone, you need to understand the makeup of it. That's where the desktop study initially comes in very handy, is to understand exactly what you're dealing with. Metamorphic rocks, the schist, the gneiss. Sandstone's pretty good to drill in. It's pretty strong. As long as it's not highly fractured, you can usually keep returns in it pretty well. So next. So how do you model this thing, right? So this is how we model it. Basically, we can model the soils on a crossing, this Mississippi River crossing. We can model it in zones, right? So we've got a zone 1 here, a zone 2 here, and a zone 3 over here. So in each one of those zones, we can model separate soil units. So in this one, we have 5 soil units. We have 5 soil units in this zone, and we have 5 soil units in this zone. So you can see up here, each one of these tables shows the soil properties that we used for each one of those zones. And we don't typically do this, but this was a Mississippi River and levee crossing, and the Corps of Engineers wants to see exactly how you modeled this thing. How you broke up your zones, what soil layers you used, what properties you used. So this is just a good figure to kind of show how we typically do it. That's why there were so many borings over here, is because this was a levee, so we had to characterize this very well. And I think some of these were actually from the Corps of Engineers.
Mark, is this a good spot to show the difference between localized hydraulic fracture and
Yeah, that's a good point, because it was asked
returns
earlier. Yeah. So, you know, I said that when we're calculating the factor of safety against hydraulic fracture, let's say we're looking at the formation limit pressure divided by the drilling fluid pressure. And that's a localized condition. We're looking at whatever the drill profile is in any given point. So when we run this analysis, we'll calculate every 5 feet. We'll figure out what zone it's in, what soil layer it's in, take those soil properties and calculate the formation limit pressure. And then every 5 feet, we'll calculate what the drilling fluid pressure should be, what we anticipate it. And then we can get a factor of safety against hydraulic fracture every 5 feet along this whole thing. So that's pretty cool. But like I said, that's a localized condition. So let's say over here, we're down here and we're in this material, and let's say it's kind of soft. Let's say it's a clay. right? Well, up here we have a sand layer. So we may calculate that down here, our drilling fluid pressure is going to exceed, let's say, the formation limit pressure. We have a factor of safety less than 1. So that would suggest that we could fracture the formation here. But another thing you can do is you can start taking a look at each one of these layers above the drill profile, right? So maybe you look at this and maybe this layer is not so good. Well, maybe you look at this layer and it's a sand layer. Well, sand layer is pretty good. It's pretty strong. We can calculate what the formation limit pressure would be at the bottom of the sand layer. And we already calculated or estimated what we think the drilling fluid pressure would be. So we can calculate factors of safety of fracturing each one of these soil layers above us. So if you take the maximum factor of safety from all these soil units that above you, you can calculate what we call an inadvertent returns factor of safety. So what you're saying is we could potentially fracture this soil here, but based on the soils above us, we have a layer here where the factor of safety is actually higher, which may prevent drilling fluid actually migrating all the way to the surface. Now you have to be careful because you have to make a lot of assumptions to draw this thing. You're simplifying things by a lot. So if you have a 1 foot thick sand layer, if this was 1 foot thick, you probably wouldn't want to model it in your model. If it's 10 or 15 feet thick, then it's probably okay to model it and you can show that it's actually, you know, if the boring, yeah. So anyway, as long as you can justify modeling it, you know, it's thick enough that it actually, because you're assuming that that thing has some aerial extent, that it's, you know, not just a thin lens of sand and disappears over some horizontal lateral distance. So this is what the analysis actually, the results in the analysis actually look like. So you can see that the green line, and what side is the entry side? Entry is over here. So the black line is the drill profile. The green line is what we calculate as formation limit pressure. Where it kind of goes off the chart, this is where it enters rock. And so one of the things that we got away from doing is trying to model what the formation limit pressure in rock is, because like I said, it's already fractured. You don't need to fracture it. So we're not going to try to estimate at what pressure you're going to start losing drilling fluid, because it's impossible to tell. You know, some formations, no problem. You always keep returns. You don't have any inadvertent returns. No big deal. And others, no matter what you do, you can't keep your returns going. So for us, it's difficult to try to put a risk evaluation on where it is in rock, other than just kind of a qualitative description. Trying to put a number to it, it's unreliable. So we just kind of have to say, well, this is the type of rock it is. It's about how fractured it is from our borings. We estimate that the risk is high, medium, low. In the soil portions, you can see that the formation limit pressure varies on both sides, depending on what type of soil you're in, what the shear strength is. The red line here shows our estimated drilling fluid pressure. So the further we drill, the deeper we get, the pressure goes up. And then as we start to gain in elevation, pressure starts to wane a little bit because the elevation, the hydrostatic pressure decreases through here. And the ratio between these two lines is our factor of safety of inadvertent returns, right here. So the red line represents a factor of safety of 2. You can see that near the endpoints, perfect example of what you're asking. Right here near the endpoints, we have factor of safety of 1.5. Over here, we have factor of safety, you know, near the entry point, they're less than 1. And you can see as we start to get some depth, the factor of safety starts to increase pretty well until we get to the rock. And then it's like, well, we're going to have to describe the risk more qualitatively than with numbers. And then just kind of provide a little bit of, let's say, explanation of what's on a design drawing, what I think is important. So you got the plan. We've looked at this several times. We got the profile. We've looked at this several times. But we have, you know, a bunch of construction notes. Any special construction considerations should be on the drawing, whether it's the minimum allowable radius that we talked about, whether it's could be work hours, it could be where the contractor is to get their water, it could be all sorts of stuff. A lot of times these are fairly generalized, but if there's any sort of, you know, construction requirements that are out of the ordinary, they should be in the notes. We've got a drill data box, which is on the next slide, or actually on the next slide. Again, this is sheet 2, so this shows the exit point, shows the stringing area back here, shows your ATWS, all that stuff. And then it shows entry and exit details. So entry side kind of shows you some details more close up, a larger scale, smaller scale. This one's maybe not a great example, but where you have a lot of utilities, like one of those slides I showed earlier, when we're picking your entry and exit locations, having these entry and exit details are kind of nice to have on a drawing. And then also an overbend detail. So given the exit angle and the size of the pipe and acceptable overbend radius, you kind of something to give you an idea how high this breakover is going to be above ground. So then here's the drill data box I was telling you about. So this is basically all the geometric information that the pilot hole surveyor, the driller, the contractor needs to know to drill this. You know, entering ground at 14 degrees. We have a vertical curve at 14 degrees at 1,250 foot radius. Our bottom tangent starts. We have another vertical curve at 16 degrees at 1,250 foot radius. End of the exit curve, and then we exit at 16 degrees. And it tells you station and elevation for each of those points. And the contractor and their people, they can recreate this in their system, in their survey system, to then survey the pilot hole. Down here, you've got the horizontal crossing length, and then the pipe length along the drill profile. So it's only about 15.5 feet longer than the horizontal distance. All right.
This contract, like, they'll typically give you a profile
What's that?
before they board contract. You give them all that.
Yeah. Oftentimes they'll provide, you know, oftentimes they'll give us back our profile, and then we'll check that it's either A, the same as what we designed, or B, if there's something in the field that requires a design change, we'll look at it and say, okay, yeah, we don't see any problem with this. You know, there should be good clearances between existing utilities. There's no issues with stresses, pullback forces, that sort of thing. So one thing to think about is weather. I mean, you know, some sites are prone to flooding. This one in particular, Trevor's getting ahead of me. Weather. Some sites are prone to flooding during times of year. You know, they used a couple sandbags to kind of help keep the floodwaters out of the pit, because they get in the pit and then it gets all over the place. Now all of a sudden you got bentonite going everywhere. You know, I've seen projects where they had to put porta-dams around the entire workspace because you had a foot or two of water outside of them. So this isn't too bad, but, you know, consider where you're putting your workspaces, when the construction is going to be done. Is that site prone to flooding? It could be a site that's not really prone to flooding, but just due to, you know, heavy rainfalls, it could just be an abnormal event. Go ahead. Perfect example of frac out close to entry. Right there. All right. Again, shallow. Another one. This is where we talk about workspace, right? It's inside the silt fence. It's inside the limits of disturbance. Therefore, it's not a problem. Regulatory agency is not going to bust you for it. So if you can, provide yourself some space out in front of the rig. If you have a frac out there, it's no big deal. Hole stability. Now, not such a problem on smaller diameter drills, you know, 12-inch, 16-inch maybe. But I don't know where this came from exactly, but large diameter drills, 36, 42-inch, 42-inch pipeline, you're going to ream this hole 54 inches. Where that hole is shallow, it's prone to collapse. So don't walk on the center line of a drill near the entry and exit, because it could collapse like that. Obviously, they put some orange safety fence around it to keep people off that area, but just something to keep in mind. And this is just, you know, hole instability. It's collapsing. And as you're pumping fluid, that collapsed material gets carried out, which allows the collapse to get bigger. That material gets carried out, gets a little bigger. You know, and this is shallow, but this can happen at depth. You know, this could happen 80 feet below ground. You just don't see it until you can get a giant sinkhole form, which there's a picture coming up later. Casing, that's something that can be used over the drill string here. They're going to rotate this in, install it with the drill rig over the drill stem. That basically helps prevent hole collapse, helps drilling fluid returns. Next one.
Oh, and also sometimes if we've got a high risk IR that
Right.
in an area that you just can't accept it, and
However,
you can.
The next photo shows that, or actually that's installed, what the casing looks like, so don't do it. But be aware that installing the casing, they typically pump drilling fluid down the casing to help lubricate it. So pumping the fluid during putting the casing in, you can frack out. So it happens.
Yeah, and depending on how stiff the formation is that you're trying to get that casing into,
Yeah.
you can drive it with a pneumatic hammer and avoid using drilling fluid, but you can only do that under certain subsurface conditions and maximum length casing.
I've seen 600 feet of casing over a drill string before on a project. I mean, that was the most I've ever seen, but that's out there. Doesn't happen often. The other thing to think about steering difficulties, we talked about that a little bit, different soils having different, let's say, steerability risks. Something to think about. Here you can see we plotted the pilot hole survey data on this profile, and you can see that there's some green dots, some blue dots, some yellow dots. So the contractor was having some difficulties steering this thing, and it looks like, they couldn't quite get the build. They were trying to steer it, and then they decided, you know what, this isn't going to work. They backed up, kicked out of the hole, and finally able to, get it on track. So different kind of soils steer better than others. And part of that's the equipment too. Some equipment, some of their bottom hole assembly we talked about, maybe use a jetting sub with more of a bend on it. That might help. Smaller drill bits can help steerability as well. Here's just another example where they ended up getting too low. So anyway, next.
Yeah, and on that one, the lower one, the contractor elected to use a mud motor, which is a lot heavier than a jetting assembly. And so they kept trying with the mud motor. Eventually they gave up, put a jetting assembly on. That was a little lighter, and so they were able to then match the profile.
I hid this because we already showed it, so I wasn't going to talk about it again. I think this is one of the last slides, so I'll try to give you guys a little break here in a minute. But elevation change is very important. So, those cards that are sitting on your table, those lengths, those are all for level crossings. There's no elevation differentials assumption. But this is not uncommon. You got a low side and a high side. This right here is what we call the fluid equilibrium point. Once this pilot hole is completed, you're never really going to be able to fill this section of this hole. Not unless this hole down here plugs up and it starts backing up. So we call this section dry hole because assuming you are keeping your turns, the fluid's always going to equalize to that point. So the condition, or basically the composition of this section of the hole, what kind of material it's in, is very important. Is it going to stand up without being full of drilling fluid? The other thing is there groundwater up here? Because if there's groundwater in this section of the hole, you can have groundwater now pouring into your hole. Seen it happen? That picture that Trevor showed earlier where there's water pouring out of the casing. Similar situation where you had some elevation differential. There's groundwater up here in this hill. Well, when you drill this section of the hole, all of a sudden you've just created a well. And now you're going to get water coming out down here, which can be a huge problem. So not only do you have hole stability concerns, you've got groundwater concerns. So if you do have, we did one for a client where there was 500 feet of elevation differential. I thought they were nuts, but it was like, well, we don't have a choice. There's the only right of way we can get through here. So, well, okay. Fortunately, we had good geologic conditions. We had a siltstone. It was fairly consistent. It was an arid area where there was no groundwater. Worked pretty good, actually. I was surprised. I thought they were gonna have all sorts of problems, but it can be done. But you don't need 500 feet of elevation differential to have a problem. You can get problems at 75 feet, and we'll see a picture of that later, where just one side just 75 feet higher than the other. You can have serious problems. So in a case like this, you probably want to drill from down here, drill a pilot from down here up to here, and then actually probably ream it from bottom to top. That keeps your fluid always flowing back to the low side. If you were to drill your pilot hole from up here and drill down this way, by the time you're down here under the river, you have all this hydrostatic head built up in this hole. And so your pressures drilling from top to bottom your pressures down here are going to be huge compared to drilling from this side. So your risk of a frac out in this river is going to be way elevated if you try to start drilling from up here.
Yeah, not only that, once you punch out at exit, all that drilling fluid's
Coming
gonna,
out.
it's gonna come flushing out and in a hurry.
And then during reaming, you know, I've seen projects where, you know, they were reaming through here, trying to get through here. What ended up happening is this hole down here plugged off with cuttings. So fluid started backing up to here somewhere, and then finally they had enough pressure that blew out whatever was plugging this hole. And it was a 54-inch hole, diameter hole. So it blew all that fluid and cuttings and everything from here and all the cuttings from down here, and it blew it out here. So they had a fountain of mud that was just coming out. It was going everywhere. It was coming out of the pit. It was going into the wetland. It was going over the silt fence. It was a mess. So, you know, on a situation like this, if you're drilling pilot hole, reaming, particularly reaming, if you start losing returns on the low side, you better fix it, because that means drilling fluid's backing up here. And when it comes out, it's coming out and you ain't stopping it. So anyway, sorry, questions? That was a long one. Trevor put too many slides in there for me. There's a lot to cover. Sorry. No questions? At least you're awake. Yes, sir.
Being bypassed by contractors or they break other reasons that were not necessarily reflective of stress and other options out there?
I haven't seen them used much at all. It seems like it's one of those things like, well, you know, the owners we've worked with plastic pipe, they don't require them. And it's, well, if you break the pipe, pull it out, re-ream the hole, condition the hole, do what you have to do and try it again. So that's a good point, though, because they could fail due to something besides just too much pull force. Who knows? They could wear out. I mean, that doesn't really answer your question, but
I started seeing some monitoring systems that are looking at real time tension. It might be more accurate, but it is more expensive. Not every service has that. A lot of plastic uses a lot more longer plastic drills.
they're pushing the limits of what plastic will do. And yeah, and that's the thing, you know, you could put sensors on a drill rig to measure what the pull force is and log it, a data logger, right? Some rigs have it. Some contractors have put the systems on their rigs. It's a good idea. I like it. One problem is with pull force, you're measuring what you're pulling at the rig. You don't really know what's being applied to the pipe, right? Remember the pullback assembly we looked at? You've got a reamer, you've got a swivel, you got the pull head. You know, if there's obstructions in front of that, then you could be pulling 100,000 pounds at the rig, but maybe only 50,000 is getting to the pipe. You don't know.
This device is actually sitting right in front of that hole.
Yeah, I've seen some research where some people took, and I didn't know there was anything commercially available, but they actually took one of those swivels we looked at, and they actually put load cells in it with a data logger, so they could actually measure the load at that swivel, so right at the front of the pull head, which I thought was very interesting. I have never seen it done, but you're saying there's something actually commercially available. Oh, so it's not.
It'll break.
Oh, so it's. I thought you were talking about an electronic device.
Yeah.
Right. Sure. $3 worth of paint, you got a new deal. Yeah. Yep. Pull it. Yep.
That's exactly what we were.
Okay.
Mechanical break. That's what we were having the issue with. Brought in an actual But they were afraid it was pulling the pipe, it breaks the pipe. Gotta mobilize, pull it back out of the other side.
Yeah.
So they were like, hey, even if the pipe is overstressed, then we can at least pull it through the entry side. He was talking about it later, but I just wanted to give you that.
Yeah, I haven't, most of the stuff we've done is bigger stuff. And so we haven't seen that required on a lot of our stuff, even some of the plastic pipe we've done. But yeah, makes sense. If I was a contractor, I might try to better my chances of getting the pipe in. So, yes. So you're talking about the drilling fluid pressure. Yeah, so when we estimate drilling fluid pressure, how do we do that? Basically, do we take a worst case scenario? Yeah, that section, like in a dry hole section like that, you're drilling through fluid pressure is kind of theoretically zero, right? Because you can't keep the hole filled. So, right. Yep. Yeah, I mean, that's certainly possible. I know it's been done in like limestone karst geology where you encounter some voids and you're just losing fluid, then go in and pump a grout, let it set, come back in, drill through it. It can be done, but it's expensive and time consuming. And then that may work, but then you drill another 50 feet and it happens again. And then you're tripping out, grouting. You could do that every 10 feet for 1,000 feet. You'd be there for a year. Or more.
Yeah, I was on a job where they tried to do grouting, and it was just really inconsistent uptake. It just wasn't consistent enough to be effective. So it did not prevent any of the problems they were looking to prevent because it wasn't predictable and consistent enough.
Should probably take a 5-minute break.
Yeah.
All right.
You guys good for 5-10 minute break?
How about 3:20? Does that work? It's 8 minutes.
You guys have referred to the 3 joint minimum a lot of times. Yeah. Is that where you say if the radius is 1,000 feet, that it's measured over 3 joints? Is that how?
Yes.
Well, so the design radius is say 1,000 feet, all right? But when they go out and they want to build the thing, they gotta steer, they gotta correct, and so they're gonna have to pull a tighter radius. If they're low of their profile, they're gonna have to correct, and so they're gonna have to make a tighter radius.
Right.
And so we will tell them, the contractor, you can steer any tighter than 700 feet measured over 3 joints of pipe.
And we have come up with a little bit too, with smaller rigs, smaller joints of pipe. Is it applicable for, let's say, a rig that's got 20-foot joint pipe joint versus 50-foot joint pipe?
Yeah.
Because three joints with 50-foot joints is 45.
Yeah.
Whereas on bigger rigs, 30-foot joints, so that's a 90-foot average.
So what you're saying is that minimum radius is applied over 3 joints.
That's right, yes.
Not on any one joint.
Correct.
So, because they'll say they can go a deflection of so many degrees per joint.
Yes.
And I'm always out there saying, I've got my drawing and it says 600 feet, 800 feet. We're small diameter people. And they're always out there going, well, that's so many degrees per joint. And I'm like, am I going to have to go back and figure? That's why I need a cheat sheet between three degrees and X number of radius.
Yeah, so you said how many, 0.7 or something?
Well, I mean, a lot of times our drill radiuses are usually 600, 6 or 8 inch pipe. So, but they'll go out there and they'll speak something back different to me. I'm telling them.
Okay.
And
He's giving you a per joint bill.
Yeah, he's giving you.
Right.
So if he said 0.6.
I'm talking feet per radius, and he's giving me deflection per joint.
Yeah.
And he's talking Spanish and I'm talking English, and so we don't know what the hell we're talking.
Well, I mean, but
We just hope that it get
if he
in.
says 0.6 of a degree, then over 3 joints, that's 1.8 degrees. So as long as over any 3 joints, consecutive segments are less than 1.8 degrees, Bill,
Okay,
it's okay.
so if they're getting off, they can amp it up for a joint
And then and then kind of cut.
and then cut back.
Yeah.
And so okay, 3, that's what I thought you meant when you said 3 joints. I thought that was the increment that you're, so if you go down and then you want to go this way for whatever, for your right of way. So how does that affect your, I mean,
No matter what plane they're in, no matter how they're steering.
it's the same radius,
It's,
right?
yeah.
And so
we have
that
a
radius is,
spreadsheet where we
that's
plug
really
in-
no worse than that, right?
No, I mean, it's
It's
whatever.
the same radius,
It's just a different plane.
right?
Yeah.
But you don't want to go this way, that way,
The
right?
problem is.
You don't want to make an S curve,
The
right?
problem is it's hard for us to check our left-right radius, right? Because of the magnetic interference.
Right, because it's based on the azimuth value from the steering probe. And the azimuth value, like I mentioned earlier, it's based on the Earth's magnetic field. And so, based on, could be a pipe nearby, it could be a road, you're drawing on a road, it can pick up like heavy steel things. And so
right, let's go ahead and I'm going to try and crank through this last bit relatively quickly. So want to talk about the elements of an inadvertent returns contingency and mitigation plan. That's a pretty standard thing we're providing nowadays. The first element to an IR contingency plan is really the mitigation or the prevention in the first place. And one of the main tools that we have to help prevent an IR is through the use of downhole annular pressure tool. As I said before, when we calculate the safety factor against IR, that is based on our, quote, anticipated drilling fluid pressures, which assumes that you have full returns, and your drilling fluid properties are reasonable. And so these things don't always happen in the field. And so the downhole annular pressure tool tells us whether or not we are having overly high annular pressures. And so we would typically, as part of our hydraulic fracture analysis, establish maximum pressures that should not be exceeded in order for our safety factors to be maintained. So the contingency plan should include those maximum pressures and then provide guidance for what should happen if those pressures are exceeded. And that may be up to shutting down operations if they can't get them down, but typically it would include recommendations to swab the hole, make efforts to reduce pressures, and get drilling fluids returning more smoothly to entry. All right. Thanks. So in addition to that, it's really a combined effort, looking at your downhole pressures, but also constantly looking at what is the condition of your drilling fluid returns, and paying attention whether or not you start seeing diminished returns of drilling fluid, or if they've ceased completely. And typically our contingency plan will provide specifics as to what the contractor needs to do if they start having diminishing returns. Again, that's going to be swabbing the hole, cleaning it out, trying to reestablish those returns before continuing the HDD on forward. There should be a section that addresses the drilling fluid rheology. We always recommend that a drilling fluid engineer be on site, be measuring the properties. There's a whole list here of parameters for the drilling fluid. And the drilling fluid engineer should be out there keeping tabs on the drilling fluid properties, keeping the drilling fluid in ideal conditions to reduce the risk. Next part of the plan is the surface monitoring plan. Surface patrols is the key there. The first thing the plan should do is describe what the frequency of those patrols should be. I don't have a rule of thumb there. That really should be based on each individual site and how high the risk is. And it may even change over the duration of the HDD. If we already know that there's a certain part of the HDD where we think there's a higher risk of IR, maybe we're in sedimentary bedrock where we think there's a high risk for unexpected fractures where it, may emerge unpredictably somewhere, we may recommend increased patrols along that particular section. The next part you want to have is a notification section. Who is to be notified in the event an IR is discovered? And so typically, that's going to include the environmental inspector, the environmental compliance coordinator, the chief inspector, the construction manager, and the project manager. And then you want to talk about what's the response in the event of an IR. Oftentimes that's shutting down the job until some type of corrective action can be made. Oh, and documentation. Obviously, documentation is key. There's typically going to have to be a root cause analysis filled out after the fact. And so you want to have all the facts and information documented to help populate that RCA. Next. Containment. You do not want to wait until you've had an IR to start looking for your containment materials. It is best for your plan to stipulate what types of containment materials should be pre-deployed out on your site, potentially at your entry-exit workspaces, pumps, hoses, containment measures, sandbags, hay bales. You want to have pre-deployed containment around your entry and exit workspace areas where you already know you've got a high risk of IR occurring. We do not typically show specifically where those containment measures are to be deployed. We like to leave that up to the contractor. They're the ones that know what equipment they're bringing in, what their ingress and egress points are. So some of this stuff we put in general and then expect a contractor to submit their own IR contingency plan showing where it's specifically going to put, how they're going to contain their entry-exit workspace. One thing I think that sometimes can be overlooked and probably one of the most common causes of releases to waters is through stormwater catch basins. All of a sudden you've got drilling fluid going somewhere you didn't expect, and lo and behold, it always ends up going down a catch basin somewhere, and had you put some type of containment there around that, you would have prevented a release. So we typically like to see that. This is a typical straw bale containment type situation for an IR event in a small stream. Another straw bale containment here, just encircling it, isolating and containing. We've got sandbags is another common method to contain an IR.
How far was that off center line?
This was about, I don't know, probably 80 feet right of center line. This is a circumstance where we were in sedimentary bedrock and it followed a fracture side hill over this direction here. And in fact, that was an area where we had anticipated there might be some concern because we have this side hill. And so we did have the contractor plan to deploy some materials out here. We didn't expect it to come out this low because this was below bedrock. We thought if it was going to come out, it'd be up here on the slope. And then cleanup, it's pretty, you're either going to have a vac truck if it's accessible to a vac truck, or a pump, or it may even be, next slide. May even be a lot of times it's just handwork. You're shoveling this stuff out and cleaning it up as best you can. And so, yeah, I mean, the plan should really address everything that needs to be on site to be able to address it and clean it up pretty quickly. Any questions about the contingency plan before we move on? Yeah. No, not typically. No. Right. Yep. Anything else? Yeah, I don't know if they technically would consider in HDD they're very commonly having to trip back out, adjust their hull, it's never a smooth. Well, I shouldn't say never, but it's commonly they're having to make a lot of adjustments as they go. And so I don't think they technically consider those abandoned holes subject to those requirements.
And it could depend too on what you're drilling under and how big the hole is. If you've reamed out a large hole already,
Under a railroad or something.
Then something like a grouting plan may end up being required. But if it's just a pilot hole, I've never seen that.
Yeah, I mean we have to do settlement calculations under railroads, and that assumes a certain overcut over your pipe, and if we end up with some kind of abandoned hole under a railroad, we might look at a grouting plan for that, or if we're capturing groundwater or something like that.
Excavating around that area, kind of being IR, but being able to.
Just daylighting and exposing it. Yeah, I mean we do that even if you're concerned about hole instability. You might just excavate that out. But typically, you're not really buying anything. If you're avoiding an IR in an area you're digging up, then you've permitted it, hopefully for disturbance, and you really shouldn't be necessarily having any advantage there if you're digging a hole there. All right, Mark, we got one last section here for basically construction observation, construction inspection.
Yeah, I think we're actually going to finish on time. So actually maybe a little early, depending how many questions you have. So this job site office, that's my laptop. That's a drill rig. And this is the best place to gather data. It doesn't always work on some projects because they have little rigs, no drill cabs, but on a bigger project that's going to be going on for a long time, being able to document the data from the drill cab is an excellent way to know what's going on and documenting things. Go ahead, Trevor. So this example of field report we typically do, we've got a table up here that talks about basically kind of a construction status table, tells us how many feet we got that day and to date how many feet we got of the pilot hole, gives us a percent complete. Same for all the reaming passes, swab passes, tells us how many shifts we've spent. So it's a good way to see kind of how the project has progressed through the different phases of construction. We've got some notes here. We've got a summary of what happened that day. And then it's also good to document things like the stencil on the pipe. Does this match what the pipe specs are supposed to be? It's happened before where, the pipe specs on the stencil did not match what the pipe was actually supposed to be. So it could cause a problem, but discovering this early on could be very useful rather than right before they're getting ready to pull the pipe. We typically like to document the tools as they come in and go out of the hole. Unfortunately, this one's covered in mud, so it's a drill bit, but you can't really tell very well. Next slide. Just kind of give you some examples. This is a pre-reamed photo of a TCI insert hole opener, split bit hole opener. So you kind of see what it looks like before it goes down hole, get a picture of it as it comes out, make sure all the pieces are still there, make sure it's all in one piece and you haven't lost anything. It's good to understand, if you notice some damage afterwards, was that there before? It means you're never going to get a perfect 3D shot of all the tools, but the other thing is kind of good to have is like a recap of shift activities, basically how much downtime did they have? And you can see here in this particular day, they had zero basically productive time and a bunch of downtime. So, you can kind of see on a day-to-day basis how much of their day was productive, how much we were fixing things, maybe were they having to re-drill a section of pilot hole, which is kind of what looks like happened here. They had to re-drill a portion of it. And then also another thing to do is kind of keep track of the hours on the tools. On a rock job, this is more important. On a soil job, not so important, but these tools have limited lifespans. These things have bearings in them that wear out over time. So trying to track the number of hours on here could be a useful tool, you know, to see that, well, you know, maybe we're halfway through this ream pass. This thing's got 200 hours on it. Maybe we should trip it out and check it out. See if the bearings still look good. When the bearings start going out, the cones get wobbly. You can start to see a gap between the cone and the arm itself. Maybe it's time to replace it. It's better to replace the tool before you start losing pieces of it down hole, and then you got to go fish them out. So keeping track of the hours on the tool is important. Then compliance with plans and specs. Are they entering the ground at the right spot? It may not even be, you know, I'm not saying this is the contractor's fault, but it's happened on a few projects where, see how this has a northing and easting and elevation on it? We've been on a few jobs where we get out there and these stakes are in the wrong spot because the design's been modified since the surveyors were last out there. So get out there before the driller shows up and sets his rig up. Get the surveyors out there and confirm with the surveyor that stake is where it belongs on both sides. So you could save yourself some headache by just doing a little legwork in the beginning before the drill rig's actually set up and anchored down. So again, you know, is a drill rig set up at the right angle? You know, that could be potentially an issue as well. So we're talking about pilot hole radius. So this is where we record basically the inclination and azimuth, the compass direction, the survey shot for each jointed drill pipe drilled. And from that information, we can calculate basically a 3-joint horizontal radius and a 3-joint vertical radius. So that's where we do that. So you can see here we have a design radius of 1200, I think, and this is a minimum, I think 1025. I can't see it perfectly, but so basically all the vertical radiuses meet spec. These are red because they were plugged azimuth values that the surveyor plugged in because there was some magnetic interference. So the text is red, but it doesn't necessarily mean it's a bust. There's a tolerance analysis where for each joint, we look at the elevation of the survey shot, how far above or below the profile it is. So this, in this case, we were 3 feet above, and then how far left or right. Here we were about 4 feet right of the profile. And remember earlier we talked about the calculated survey using the Earth's magnetic and gravitational fields. That's the calculated survey. And then the survey that comes from that wire that we looked at, that's the secondary survey. This was a true track system, so it's a true track survey, but in general, it's called secondary survey. So record both of those, and you can see there's some discrepancy between them. But the surveyor can use this data to kind of help rectify some of this data. If there's any magnetic interference, he can use this data to kind of help fix this data because this is more accurate. And then we have downhole pressures over here. So, you know, for each joint, what was our annular pressure and what was the maximum? So we kind of have a recommended maximum versus maximum observed. So you can see that our pressures, we're doing pretty well over here. This is a penetration, basically penetration rate analysis, or actually it's a time per joint. So this is for a drill, Hominy Creek. So for each joint on the pilot hole is how long it took to drill each joint. And then for the first reaming pass, which was 20 inches, how long it took in hours and minutes to drill each joint. So you had a 4.5-hour joint on the 20-inch ream pass, but it only took 38 minutes to drill a pilot hole. So again, this is kind of useful. You can kind of see where, you know, on that pass, that joint took 4 hours and 38 minutes, where it took 40 minutes on this pass. So why is that? Is that just some sort of weird anomaly? I'm not sure. I wasn't there. Ursa was probably there, but next one. So this goes back to talking about annular pressures, monitoring the pressures, mitigating for high annular pressures. And so these are two different projects here where we had a recommended maximum and we have a maximum observed. And you can see that right here, we're good, 22 versus 25. Here, okay, now we're starting to exceed what the recommended maximum pressure is. Well, the contractor basically tripped out the tooling to help clean the hole, pump some more fluid, get cuttings out of the hole. And then after tripping back in, our pressures are good again. So, you know, you can take proactive measures. You start to see your pressures increase too quickly, You can see these are starting to increase faster than these are increasing. You can take proactive measures to get your pressures down to something more reasonable. Same thing here. This is just another example of the same thing. The contractor tripped out, cleaned the hole, pumped some fresh fluid, got cuttings out, reduced their pressures. And then this is just a drawing showing that, you know, it's good to be able to plot the survey data on a drawing. Just kind of give you an idea of where the pilot hole is. So how far in you are, what you're under, what you're drilling under at the moment. You know, you may be drilling under a railroad. So by being able to plot this in real time, you kind of have a better idea of where you're at, both in depth and where you're crossing and what kind of geology you're in based on the borings. So what can go wrong? So this is just a collection of photos of things that kind of went sideways. So we've talked to some people here individually about this, but this is where you had dry hole. There was only 75 feet of elevation differential. We had designed this drill profile where they can install large diameter casing through that section of dry hole, but we recommended it actually as part of the design. The client said that they didn't want it. They figured if the contractor thought they needed it, the contractor would bid it and put it in their bid. Well, that didn't happen. This happened instead, created a big problem. They actually had to, this is Interstate 15 in Salt Lake City. They actually had to close one of the lanes of this at night because they were worried the freeway was going to cave in potentially. It's not something you want happening. It doesn't look good.
Yeah, that interstate actually ended up having, I believe it was 5 of the rigid concrete panels spanning a free gap. So thank God it was rigid concrete and not asphalt. And I was shocked at how strong they were to span it.
Same problem, same issue, elevation differential. This is dry hole section. Now you've probably destroyed, I don't know, somebody's driveway maybe it looks like. I'm sure this landowner is not super happy at this point. Tools wear out. You know, they probably weren't getting very good, you know, footage with this thing until they tripped it out. And you can see what I was telling you, when the bearings wear out, you can see the cone is separated from the arm. The bearings are shot. This thing's about to fall apart. Gravelly soils, this fly cutter, they tried tripping it out and it was hanging up on a bunch of gravel downhole. Like, remember Trevor said, you know, you got these big chunks of gravel. That drilling fluid does not carry that stuff out of the hole. So it just sits down there and accumulates. And, you know, you can get hung up. Broken hole opener, here's where cone actually did fall off. Looks like that one fell off. Looks like that one fell off. Bearings wore out. Once the bearings wear out, the cone falls off. Now you go fishing. And depending on what you're in, you know, you may not have very good success getting that stuff back.
Or maybe tell them what fishing is.
What? Fishing? Oh, going fishing. You got to send some down hole to try to get it back out. And I'll show you some pictures of tools. Fishing basket. It's basically just like a barrel-shaped thing, some slots cut in it. It's got like an auger flight type deal in here. So when you turn it to the right, you'll pick stuff up, and then you can trip it out. This has been used successfully. We were on a job in New Jersey. We were able to get a couple cones out with that thing. Smashed in barrel reamer, again, gravelly conditions. Go ahead. Busted tube on a jointed drill pipe. You know, on rock crossings, big inch, that tooling takes a beating. You know, it's just fatigue. You know, this stuff takes a beating, and so eventually it breaks. There's an overshot. So let's say you're drilling pilot hole and you twist off your drill string. You don't have the benefit of the tail string we talked about later to go the other side and just yank it back. So this, you get over top of the drill pipe with the overshot, and there's a kind of like a spring steel thing that expands as it goes over the drill pipe, and then when you pull on it, it contracts down and hopefully enough to clamp onto that pipe, and you can pull it back out. So next. This is a frac out. You can see it started up the hill, came down the hill, kept going down the hill. You know, I'm sure whoever owns this isn't too pleased. So this is just kind of a collection of what goes wrong. Is frac out into the water. This is in Boston. I'm sure those people were happy. Keep going. So this is an interesting story I think you'll like. Contractor decided to shut down for Thanksgiving, and they weren't finished reaming the hole yet, but they didn't want to leave their drill pipe in the hole that long because they're afraid it might get stuck or something. So they tripped everything out of the hole. They come back after Thanksgiving and start pushing a barrel reamer, just a barrel with some teeth on it. They start pushing that back through the hole. Well, eventually, torque started to get really high. The resistance really started to get high, and they just get, the hole maybe caved in some. So they just kept going. And finally, they got stuck. So we got sent out there, one of our guys, and he's like, well, I'm going to go walking through the woods. Comes upon this. This is not the exit point. They essentially pushed that barrel reamer out of the ground somewhere between entry and exit. Pushed it, so it basically came out probably somewhere around here. It was shooting mud everywhere. Kept pushing it up through here, next one, and eventually got stuck in a tree. So, they were kind of trying to take a shortcut. The best thing to do would put a bottom hole assembly on this with a steering tool, run it back through the hole, make sure you're following the hole with your old survey data, compare the two sets. But, shortcut leads to stuck reamer in a tree.
Hey, were they going to clear an easement, or is it going to be woods? Is that?
That would just be woods, yeah. It was like a wetland, swampy area in Arkansas. Yeah, gravelly soil, smashed in pole head and pipe. Keep going. Okay, so we saw the other half of this earlier, but this, you look at this, you're like, that looks like something weird's going on here, but you can't really tell until you look at the next photo, which is that. So this is what happens when the swivel locks up. As part of the pullback assembly, you've got that swivel that allows them to rotate the reamer in front of the pullback assembly. When it locks up and you're rotating, well, now all of a sudden that pipe starts to rotate, and that's what happened. Some owners require that the swivel be load tested prior to use, particularly on big, high risk, complex projects, big inch pipe, not the little stuff, but just, looks like a roller coaster, but just, again, things that can happen. Go ahead.
Were they able to straighten that out and continue using that?
I have no idea. I wasn't there. I'd have to ask the guy who was. I don't know. It could have yielded the pipes, or it was kind of permanently deformed, I imagine. It was messed up. Pneumatic hammer for hammering a pipe in. If the pipe gets stuck, this would be okay if you only had to go maybe 100 feet to get the pipe through the hole. But, contractors have gotten stuck a couple 100 feet in the hole, decide they're just going to try to hammer it the rest of the way, which then usually ends up badly. So, if you're only a couple 100 feet in the hole and get stuck, you should be hammering the pipe back out and not trying to hammer it in. So, again, stuck pipe, shackles, big cables, snatch blocks, and a big winch in the next photo. So, when you get stuck, you got to resort to extreme methods to try to get the pipe back out. They got a side boom and a dozer, and I forget what they call these things, but it's a winch, big winch, all strapped together to try to pull that thing back out of the hole. Anyway, those are some of the things that go wrong, and we're 20 minutes early. I think that's a 9, or is that a 0? Oh, 10 minutes. Questions?
The cost of adding a rocket to a drill, is it the amount of extra time? It's very expensive, right? So is it the amount of extra time? Is it the costs of the drill itself? Is it the risk of losing the drill head, or is it a combination of all those things?
I'd say largely time. Secondary would be tooling cost, because the tools are a lot more expensive for rock than they are for soils. Like I said, some of those contractors, they build their own fly cutters and different things in their shop. This can be pretty cheap, but time. I mean, I've been on a job where in a 12-hour shift, we got reamed 60 feet on a 5,700 foot drill. Yeah, it took 9 months to complete. So versus a soil drill the same length, you could probably do in 2 or something, So anyway, anything else? Questions?
Yeah, just to respond to that, getting back to balancing the risk of, an IR, maybe being in soil above the rock versus getting down into the rock and potentially having a lower risk. You know, I was talking about some of those more expensive laboratory testing and geotechnical parameters, you know, spending an extra 10 grand on geotech to prove out potentially staying in the soil versus getting down into the rock. That's where that could pencil out pretty well.
Yeah. Well, if there's nothing else, I think maybe we're done.
Do y'all have a coding
Yeah.
or anything that y'all would recommend?
No, I mean, usually the pipeline companies will have their own kind of coding. You know, they do their own testing, evaluations. We stay out of that. Let the pipeline companies decide what they like the most based on their experience. Yeah.
One last question around, so for us, as soon as we have our inspectors, they have to verify that you hit rock before you hit rock head on. A lot of them don't go through like any vigorous training, so and myself included, like I want to know exactly, you know, besides the different sounds, and vibrations, and the fact that you're just not pushing forward. Do you have any other, you know, recommendations of things that you look for to verify, yeah, you're definitely hitting rock?
It's largely just penetration rate, you know, and you know they can kind of fake it, I guess, if they really
That's what
wanted
all
to.
inspectors say, oh, you're
Yeah.
making it, it's a lot more money, but, you know.
But you know, I mean, if you can see, go into the drill cab and see how hard they're pushing or how hard they're pulling, you know, and you know that the tool's not just wore out, then you know you might, well, yeah, they're not making any progress, you know.
Yeah, and if your geotech is somewhat decent, it shouldn't be too big of a surprise when you're either getting into rock or not getting into rock.
Yeah, I mean, we do a lot of, I mean, even like services, small stuff, like
Yeah, you're not getting the, yeah.
even that, you know, like $50, but $200.
Yeah, you don't need much of that, and it makes a huge difference.
Well, you know, and to that point, I always think the geotech pays for itself, because what happens is when the contractors don't have geotech when they're bidding, they tend to bid worst case, and so you're going to pay for it through the higher bid costs. I mean, it may cost 12 grand or 10 grand for geotech. I can almost guarantee you're going to see that at the bid side from the contractors if they're blind.
Yeah, on a competitive bid basis with good geotech, you probably get a lot tighter bids. So, you know, rather than some that are way off over here and some off over there, and allow you to choose better. Yeah.
That is worse, yeah.
All right. I guess we're done. Thank you for joining.